Testing, testing, 1, 2, 3. Okay, a very good morning, everyone. Hopefully you can hear me okay. Apologies for the technical issues this morning. I'm not sure why Zoom chose today again in order to be frustrating and annoying, but there we are, it did. So on to today's session. So as I mentioned last week when we last met, today's session really is kind of the start of where your sort of modeling and data science journeys are going to begin, because up until now in October we were teaching you all of the kind of fundamentals, all the bits of stuff that you would need to know in order to be able to do this kind of stuff, mainly the Python training, so mainly teaching how to program and specifically in Python. But also some stuff around free and open source development and version control, and a little bit of an introduction to things like the modeling cycle, the modeling process, etc. as well. But from this point forward, we're going to put all those skills to good use. And so now comes the time at which you're now going to use your newfound skills in order to build models and build machine learning algorithms and all the other fantastic stuff that you're going to be able to do throughout this course. And the other thing to say is that you need to now start having one eye to your projects and your project proposals. So basically over the next month, we're going to be showing you, well, it's really sort of next 3 weeks mainly, you'll be introduced to a lot of these new techniques, and you'll have a lot of introductory sessions for each module that will basically give you a bit of a better idea. So in the very first session we had, right back at the start of HSMA, I sort of very quickly went over, here's the stuff that we're going to cover in the course, and here's basically what we mean by discrete event simulation and system dynamics and all the other things that we're going to teach you. But we didn't really go into much detail at all about those things. So in these introductory sessions, you're actually going to be learning much more about how these things work and the theory behind them, and then you'll gradually go into showing you how you actually build these things that we're teaching you using the various packages. So SimPy, for example, today. The idea of the introductory sessions is to give you a better handle on what these things look like and how they work, in order that you can come up with some project ideas. So I will be posting more information about this on Slack in due course, but just to give you a heads up, what we'll be expecting from you is to put together a 2-minute video project pitch. And I will show you some examples as well. I'll show you some examples of what successful pitches we had from the round last year. And basically it's just a 2-minute pitch that details the project that you want to do. And there's various things that we'll be looking at in terms of which projects to take forward, but the two key things that guide our decision making are: A, is this doable? And B, is it impactful? So is this something that you could do and you know, the methods you're proposing, is that going to work, and is it doable in the time frame? And is it something we should care about? Is it something that is going to be important for the organization and service users? And also this year in particular, because we've got a national cohort, we're also going to be, and we've got the integration of health, social care and policing as well. We're also going to be encouraging, wherever possible, projects that collaborate and work together, either cross-organization and or cross-sector. And so you should also be thinking about potentially collaborating on these projects as well. So I'm flagging that up now because basically over the next few weeks, you're going to need to be thinking about your projects. You'll need to be thinking about speaking with relevant stakeholders in your organizations, speaking with your manager, whoever it may be, in order to come up with these project ideas based on the sort of stuff you're going to be seeing over the next few weeks. And hopefully that should be firing off some ideas. I'd also strongly encourage you all to be on Slack and talking to each other and sharing some ideas and sort of tossing ideas around, because if there are sort of collaborative proposals and people that are looking to sort of tackle common challenges, that would be a great way to do it, and also to get feedback about some of your thoughts. So more details will follow. But just to point out, it is a month today, the 2nd of December, when I believe that is the deadline for submitting these project videos. So you haven't got long. You don't need to do much. It's only a 2-minute video, but it needs to have some key information within that as well. So use these next few weeks now to start thinking about what can you do, what might be your project, what how are you going to use these newfound skills. Now you're not going to be able to do that right now unless today you find that you know, discrete event simulation is exactly what you need. It may well be for your project, but keep an open mind as well. So over the next few weeks, you're going to learn about all the different stuff: natural language processing, network analysis, machine learning, agent-based simulation, all of that stuff you'll be introduced to over the next few weeks. So absorb that information, and then at the same time be thinking about and talking to people in your organization, and seeing if there are particular problems that you think some of these methods can tackle. So more information to follow in due course, but this is just a bit of a heads up to say now is the point at which you'll need to start thinking about your project proposals. Okay, so that's enough of that for the moment. As I say, I will provide more information about that in due course. So let's go back to today, and let's start talking about discrete event simulation. So in the very first session, I did briefly mention discrete event simulation, and I said that it's basically a modeling technique that we use as a way of modeling queuing type problems. So real world systems that have some sort of queuing within them. Now, basically in a discrete event simulation, we have entities that are flowing through our system, and they flow through and they are queuing for, in some way, discrete sequential processes that use resources. And so in healthcare, for example, it's very often used to model processes, patient pathways. So you might say use a discrete event simulation model to model what happens to patients when they arrive at the ED, or what happens when they arrive at a particular clinic. They will go through a set of processes, and they might sort of branch off and do different things depending on the different characteristics of those patients. You know, what their condition is, whatever it may be, severity. But in essence, they will be going through a set number of processes, and each of those processes will consume some resources of some kind, and they will be waiting at each stage in order to have that process undertaken. So because of this, discrete event simulation is really useful when we want to ask what if questions about the process and about pathway changes, or potential pathway changes. So let's look at an example. So let's just take the simple ED example. Our discrete event simulation might capture something like this: patient arriving into the ED, they wait, they queue here. Then they have a process here where the patient is booked in. That's a process that requires a receptionist as its resource. Then they queue for this thing over here where they get triaged, and that consumes a triage nurse resource. And then different things might happen after that triage. It might be there's no further action, or it might be that they need to be seen by the doctor, in which case they'll flow over to and queue for this process where they are treated, and that may need a treatment cubicle and probably a doctor resource as well. And different outcomes might come out of that. So it might be that unfortunately they die, or it might be that they're discharged, or it might be they're admitted. And if they're admitted, we might want to capture further processes, etc., etc. So at each stage, we're thinking about the system in terms of the entities that are flowing through. And remember, they don't have to be people. Very often they are, but they don't have to be. That you have entities flowing through, different things are happening to them. That's the processes. Resources are required for those processes to happen. And for each process, the entities are queuing, waiting for their turn for that process to happen. So let's break this down and think about the individual components of a discrete event simulation. So I've already mentioned entities. So entities are your things that are flowing through these sequential processes. And as I say, they don't have to be people. Very often they are, but you might also, for example, think of your entities as telephone calls. So you could create a discrete event simulation of a telephone call system. and how people are queuing for an advisor, or going off in different branches, pushing different buttons, different options, go down to speak to different people. And that's very commonly done. You might be thinking about test results, and thinking, so your entity in that case is not a person, but a kind of vial of blood, and it might be that's flowing through these different processes. So there's all sorts of different things that could constitute your entities. It's whatever the things are that are flowing through these processes. And you may have a mixture of entities within the same simulation as well. Then we've got generators. So generators are basically the way in which entities enter the model and come into being. So these are kind of the entrances to your model. So in the case of the ED, for example, we might think about there might be different ways in which patients can enter the ED. So they might be brought in by paramedics, they might self-present at the ED, etc. Now, it may be that we don't need to capture those separate ways of coming in. It may not make any difference for the model. Remember back to the first session, we talked about we're trying to capture kind of the level of detail that would make a difference for your question. So you only go as detailed as you need to in order to answer your question. But it might be that those things are important because they'll have different arrival rates, for example. That brings us neatly on to inter-arrival time. So an inter-arrival time specifies the time between entities being generated, i.e. Arriving into our model. And I'll talk a little bit more about inter-arrival times in a bit. Then we have activities or servers. So these are the I've talked so far about processes. In discrete event simulation language, we refer to them either as activities or servers. In this course, we tend to call them activities rather than the server nomenclature, but you may see servers as well mentioned in discrete event simulations, and it basically just means the same thing. It's the stuff that's happening to people. It's the stuff that these processes they're going through, and we typically refer to them as activities. So these are the things like triage, treatment, ward admission, whatever it may be that's happening. And with each of these things comes an activity or server time, and that basically represents the amount of time it takes for an activity to happen to an entity. So, and we typically would randomly sample that from a distribution, which we'll come on to, in order to kind of approximate real life variability. And we've already talked about that a little bit on the course. Then we've got resources. So resources are the things we need for activities to take place. So, we talked about the nurses for the triage, or the receptionist for the signing them in at reception. And also resources may and very often are shared between activities. So, you don't have typically a nurse who's just doing that one thing. They may also be doing other things as well, and so the resourcing is not is very often shared across your processes, across your activities. Sorry. Then we've got queues. So queues are basically where your entities are held whilst they're waiting for an activity until that activity has capacity and the required resources to begin. And then lastly, we have sinks, and they're basically the exit points of the model. They're the opposite of generators. The generators bring them in, and sinks are how they leave. And I'll talk a bit more about all of these things as we go on. So let's look at our example again that we just looked at before. So in this case, patients arriving at ED, that's our generator. So that's how new patients are coming into the model. Then we've got our various queues as we wait for each of these processes to happen. We've got our resources, our receptionist for this activity, our triage nurse for this activity, cubicle for this one, etc., hospital bed. We've got our activities themselves, so patients being booked in, triaged, etc. And of course, our entities are patients in this example. Our activity times are the times they spend in these activities. So the time being spent being booked in, the time being spent triaged, the time spent being treated, etc. And then we've got our sinks, the various different ways in which they can leave the model. And remember back to our first lecture where we said that an exit point in a model doesn't necessarily mean they've left physically that system. So if you're modeling an ED, you may only be modeling part of that ED, and so the part that's of interest for your question, and actually they may well leave the model, but that doesn't necessarily mean they've left the ED. So you might, for example, only be modeling the triage bit, in which case your sink might be here and you won't care about what happens after. And so don't necessarily confuse a sink with they physically left that real world system. Okay, so let's go through each of these things in a little bit more detail to really help you to understand how you would design and build a discrete event simulation. So we've talked a lot about entities and what our entities may be, and say very often they'll be patients or service users, but not always. Now, each entity may have certain attributes that will help determine its journey through the model system. And you're probably already connecting the dots a little bit here when thinking back to the object-oriented programming lecture that we did last week, and how this may indeed work as we're going forward. But we can think of our patients as holding pieces of information that will determine what their journey in our system looks like. So it might be that they hold information about whether they're going to end up going down path A or path B, or how long they as an individual are going to spend in an activity, or what their priority is going to be for a queue, because you know, you'll have patients coming in with different priorities. And so that kind of information will then help us within our model. So we might have a patient, for example, who's got these three attributes that says their priority is high, the ED stream they're going to go down is the majors stream, and their probability of being admitted is 0.8. And that will help us when we come into the model. So the model, their priority is high. That may it may be that they jump to the head of the queue in our particular model. If their stream is majors, that will determine that they go down this path in our model, and it will also the probability that them being admitted will determine the likelihood that they are going to end up down at this point here, which may be a sink or it might be another process, rather than at this point here. So we can have lots of information that our entities carry through with them in the model in order to determine their journey. And as I said, there may be more than one type of entity in the model for the same time. So you might have patients in a clinic. You may also have their test results flowing through in the same model. You might have phone calls into the clinic, and they're all entities we may want to capture when doing a model of a clinic. Okay, let's talk a little bit about generators and inter-arrival times. So we said that generators are the way in which new entities are brought into being, are created, come into our system, the entrance points. The inter-arrival time goes hand in hand with that. So the inter-arrival time specifies the rate at which generators bring new entities into the system. And you'll hear a lot of talk about inter-arrival times in discrete event simulation modeling. So the inter-arrival time specifically represents the time between one entity being generated and the next one being generated. Okay, so they might be fixed. So it might be in some cases that you have a fixed inter-arrival time, that entities arrive at a very fixed interval. There's no variability at all. But in reality, you're probably going to have some degree of randomness in there. You're going to have some degree of variability. So usually inter-arrival times are sampled from a distribution stochastically. So we use this terminology, sampled stochastically. Sampled basically just means drawn, and stochastically just means at random. Okay, so sampled stochastically from a distribution is a common thing that you'll hear in this world, and that will allow us, as we talked at length in the very first session, about was to this way of capturing variability, even if it might be a very small amount of variability. But as we looked at in that example, we saw that even a very small amount of variability can be important and can have a knock-on effect on our system. Very often, an exponential distribution is used to sample inter-arrival times, and that's a common thing that you will see. So very often, as your starting point, at the very least, you probably use an exponential distribution, unless you had evidence to the contrary that the rate of your arrivals is following a different kind of distribution. You can have more than one distribution used for the same generator. So, for example, you might have different distributions for different times of the day, because the rates at which people arrive may differ at different, and will often differ at different times of the day, or different days of the week, or at different months of the year, where you've got seasonal effects. So you can capture all that. You can have it so that the model will sample from different distributions depending on what day it is, what time it is, etc. And as I said, you can also have more than one generator in the system, and they can use their own distribution. So you might have a generator that samples the inter-arrivals of patients arriving at the ED self-presenting versus the rate at which they're coming in by ambulance, for example, and they're likely to be different. So let's imagine, let's break that down into an example. So we might have a couple of generators in our system. We might have a generator that generates arrivals into the clinic, and we might have a generator that generates phone calls into the clinic. We take the arrivals into the clinic as the example. Essentially what we would do, the first thing, we would randomly sample the time to the first arrival. So from the time of the simulation starting to the time at which the first arrival will happen, and we'll call that T0. Then we will wait for that time. So basically from the simulation start plus whatever time we sampled here. So let's say we sampled 3 minutes, so that we would wait for 3 minutes to elapse in our model from the time that the simulation started. At that point, the generator would then generate an entity. And then at that point, it would then randomly sample another time, which would represent the time to the second arrival. We'd wait for that time. So if we then sampled 5 minutes, we'd wait for the 8-minute mark. And then at that point, it would generate an entity. So each time it's generating an entity, and then it's sampling how long it has to wait before it generates another entity. And so what it's doing each time is, if we use the exponential distribution, it's randomly drawing, randomly sampling from this exponential distribution, picking a number that will represent the amount of time until the next patient arrives. Okay, let's talk about queues. There's quite a bit to talk about about queues in discrete event simulations, not least because they are, as I said, models for queuing problems. So as you would expect, there's quite a bit to talk about in terms of queues. So each activity in a discrete event simulation, as we've said, has an associated queue. And this queue is kind of a holding place for entities whilst they wait for the activity to become available. Now, those queues may be real physical queues. So you imagine if we are modeling, for example, a supermarket checkout where people are physically standing there and waiting in a queue. But the queue doesn't necessarily have to be like that. A queue could represent somebody on a waiting list, or somebody that's on the phone waiting to get through, and they're in a call queue. So it doesn't necessarily have to be a physical queue where people are sort of standing literally and waiting, or waiting in a waiting room, whatever it may be. So just think about a queue in discrete event simulation terms as being you are waiting your turn for this activity. Now, each queue has an associated queuing policy. Now, the queuing policy determines the order in which your entities are going to be released from the queue into the activity. Now, there are various different queuing policies, but the two most common ones that you will need to worry about are these two here, which is first in, first out, FIFO, which is basically entities are seen in the order they arrive, and that's the default. Okay, so if you arrive and then somebody arrives behind you, you're seen before they are. Okay, so that's the default queuing policy, first in, first out. But you may also, particularly for the kinds of sectors that you are working in, you may want a priority-based queuing system where entities are seen according to some kind of priority attribute. So I said the entity may carry along some information about their priority or their condition, and we can use that information to see those with a higher priority first, so they get released from the queue before those with a lower priority. And very often, if people have got tied priority, then that would be resolved using FIFO. So then in which case it would be whoever arrived first. But of course, you could set up whatever you like. You could have it with a BTR breaking ties randomly, however you want to do that. But these are the two most common queuing policies that you're likely to use for the kinds of models that you're going to be building. Now, of course, when we're dealing with human beings as our entities, one thing we need to factor in is the way in which people behave. Because, of course, when they're waiting for things, they will have certain behaviors depending on what they're waiting for and various characteristics of the queue. And so sometimes, not always, but sometimes it's important not to just assume that your queues in your system are going to run exactly as planned. In fact, we may need to model behaviors where either entities either stop waiting or they switch queues or they never decide to join the queue in the first place. And there are three key queuing behaviors that are worth mentioning here, which is reneging, bulking, and jockeying. So let's imagine we've got our production here. Everybody is queuing for an audience with Dan Chalk production. They're queuing for the box office. Clearly, I don't have enough slide space to draw the lengths of these queues as they would be in reality. So we will just have to use our imaginations there. But I can use this to demonstrate these three concepts. So first of all, let's start with reneging. So reneging refers to an entity removing themselves from a queue after a certain amount of time has elapsed. So in other words, they're not prepared to wait any longer, so they remove themselves from the queue. So you might have somebody who's standing in the queue for the supermarket, and then they're not going to wait any longer, or it might be that you've got a test sample as your entity and it's no longer viable. And so it has to effectively be removed from that queue, because wherever you've got an aspect where time is going to play into whether they can still continue to queue, then we've got this concept of reneging. Associated with this, we've got this idea of bulking. So reneging refers to basically an entity removing themselves, or they might be removed by someone else because it's too long a wait, but usually it's removing themselves. But whereas bulking, they basically never enter the queue in the first place, because essentially they might see the length of the queue, or they see there's no capacity in the waiting room, so they never join that queue. Essentially, they are horrified by this. They're not bothering to keep. I mean, clearly somebody would never do that if for this particular production, but that's like reneging, where somebody's basically decides they've had enough. Bulking is kind of similar, but they never go into that queue in the first place, so they renege before they join it, essentially. And then we've got jockeying, and jockeying is basically where an entity decides to switch queues in the hope of queuing for a shorter amount of time. And so you might think about, you've probably seen jockeying behavior. You may have undertaken jockeying behavior, where essentially, you might be in the supermarket and you might decide to switch tills because you think that queue over there seems to be moving a bit faster. So I'll switch and go over there. That's jockeying. That's where people are moving from the queue in which they originally joined. Now, you probably won't find too many examples of that in the kind of stuff that you'll be doing, although you may. But it's worth bearing in mind jockeying alongside these other two. But certainly reneging and bulking, you may have a lot of scenarios where those kinds of queuing behavior are important to capture. Okay, so that's queuing. Now let's talk about activities and activity times. So we said that each activity in a discrete event simulation describes a process, and it might be that's a very simple atomic task like place letter in tray or whatever it may be, or it might be a set of tasks bundled together. So the triage process is not atomic. There'll be all sorts of things happening as a patient is triaged, but we decide to bundle that up for the purposes of our model and say it's the bundle of stuff we're calling triage. And how you bundle stuff up or go the other way and make them atomic very much depends on what you're modeling and the level of detail you need, and all those considerations that you need to make that we talked about in the very first session. Now, for an activity to take place, we need two things to happen. We need an entity to be drawn from the queue, and we need the resource of the required type and the required number to be available. Those two things need to happen in order for an activity to take place. We need the thing that is going to do the process, i.e., the resource or resources, and the thing unto which the activity is going to be done, i.e. the entity, which might be the patient or the test result or whatever it may be. Both of those things need to be ready and available. Once those conditions have been met, then the activity begins. And the entity and the resource or resources, depending if you've got more than one, are then locked into place for an amount of time, and that's referred to as the activity time. So the activity time basically holds the entity and the resource or resources required, so they can't do anything else. They are locked in with each other for the length of time that that activity will take. And although in some cases you might have fixed activity times where they will always take a set amount of time, usually, as you can imagine, in real world processes, that's probably not the case for most things. And there will typically be some variability, even in things that have or should have, fairly fixed times. You will usually find some degree of variability. So we sample from a distribution, much as we do for inter-arrival times. And for process times, activity times, we typically sample from either an exponential or a log normal distribution. Now, there are other distributions that can be used, and later in the course, you'll find out about distribution fitting. Sean will take you through some stuff in R that allows you to fit your data to distributions and work out what sort of distribution your data is most closely fitting. But typically, good rule of thumb is exponential distributions for arrivals, inter-arrival times, and either exponential or log norm distributions for your process times, your activity times. So if you've got no other information, that's a good place to start, because typically that's what's used. And usually these are pretty good representations of the shape of your data. So let's think about that in terms of a real world example. So imagine we've got our start GP consultation process here. In order for that to happen, we need the patient to be ready and we need the GP to be ready. Once both of those things are true, they can both be pulled together, and we can randomly sample an activity time. So here I'm sampling from a log normal distribution. We sample whatever time, so let's say it's 5 minutes. Then those two, the entity and the resource, are then locked in place and held together for the sample time, so 5 minutes, until that process then ends, and at which point the GP and the patient are then released. So it might seem a bit weird that I'm talking about it in those terms, but this is the way in which you need to think for a discrete event simulation. And this will help you when we come later to look at SimPy and how you build a SimPy model, to think about it in those terms, that effectively you're holding your entity and your resources in place for an amount of time, and then they get released. So you're constantly holding things, grabbing them, holding it, and then releasing after an amount of time. And that's basically how these things work. Let's talk a little bit more about resources. So we said resources are the things that we need to undertake an activity. It might be that an activity just needs a single resource. So, the example we just looked at with a GP consultation, we just need a GP resource. I suppose you could argue you also need the GP's room as well, but usually you wouldn't model that unless you've got some sort of shortage there where they may be fighting over rooms, and therefore you need to model that too. But it might be that you need more than one resource for an activity to happen. It might be more than one resource of the same type, so it might be you need 2 doctors. Or you might need multiple resources of different types. You might need a doctor and a nurse, for example, for an activity to happen, plus a bed. An activity might, in some cases, not require any resources at all, or nothing that you need to model. And that's possible, but just think very carefully before you do that in a model, just to make sure it really is either in the real world resourceless, or for the purposes of what you're modeling, it doesn't matter. You're not you're not needing to model resourcing in any way, because you might have an abundance of that resource. There's no issue of that shortage, and it won't cause any issues elsewhere, for example. But you just need to think very carefully before you go down that route. And as I said, resources might be people, so staff, things like doctors, nurses, police officers, whatever it may be, and they might be stuff, so things like beds, test equipment, detention cells, whatever it may be. So if you think of resources as being staff and stuff, that will help you to think about what are the things that we need for that resource to happen. And as I say, at the same time, you also need to be thinking about your level of detail considerations in your model. So technically, in order to see the GP, you need the GP there, you need a room, probably need a chair, they need their stethoscope, but you probably don't need to model most of that unless there is some sort of competition going on for the resources or some sort of shortage. You probably just need to model the fact that you've got a GP resource that's being used. Now, I mentioned before that resources can and often are shared across the system, so they might be required for more than one process. So what that means is that if you've got a resource drain in one part of the system, that can have a knock-on effect in another part of the system. And so that's very often the sort of stuff that you will see emerge from a discrete event simulation. Now, once you've specified all the required resources you need for an activity to happen, all of those resources need to be available for that activity to take place. It might be the case that you've got some activities where, for example, you might have one doctor as the minimum, but if you've got two doctors, it might speed things up. And so you could model that. Be aware, though, that's rarely a linear relationship. So it doesn't typically mean if you've got two doctors, they can see the patient twice as fast. But it might mean that they're able to do something that whilst this doctor's doing something else, and it might speed up the process ever so slightly. So that's worth bearing in mind as well. So let's think about an example here. So we might have our resources being nurses, might have a couple of nurses, a doctor, a couple of cubicles, a few beds. So we've got our staff resources here and our stuff resources here. And these resources may be shared across the system. So for triage, we need a nurse and a cubicle, but nurses and cubicles are also required when we're taking bloods, for example. And the diagnosed patient process, the activity will need a doctor and a bed. So thinking about what your staff and stuff resources are, and how they're shared across the system. Now, another aspect of resources that we need to think about is resource availability. Now, it might be the case, and you probably think of lots of examples, where a resource might be unavailable for an activity because they're working not because you're waiting in the queue for them and they're seeing the person in front of you, but because they're working on another activity in the model. So like here, where you're waiting for triage, but the nurse is off taking bloods. Or it might be that they're unavailable for other reasons. They might be doing stuff that is not going to be captured in your model. Okay. So it might be that the doctor keeps getting called away because they need to go off to another part of the hospital or whatever it may be, and we're not modeling all that, but we need to some way capture the fact they're not available. Or, of course, it might be they're not available because they're not working. They're not on shift. There may be shift patterns. Now, as with all of this kind of detail stuff, as the modeler, as the model designer, when you're building your conceptual model, your design, your blueprint for the model, you need to be thinking about what detail you need to include in your model. So you need to think about what will happen when the required resources are not there, either because they're off working on something else or they're not on shift. And that's all part of your model design, your conceptual modeling process, when you're working with your stakeholders, with the people that are involved in that real world system. So if a resource isn't there, then do entities wait until the resources are back, for example? Is it not a problem because another resource replaces them? So there's always a resource available of that type, so it doesn't matter, etc., etc. So you need to think about what would happen in the real world and how you're going to capture that. If you do need to capture unavailability in some way, then there's an easy way to do that in SimPy, and that's basically that you have a priority process, a priority activity that grabs the resource you want to make unavailable, and then will keep hold of it for a length of time. So if we imagine we've got our doctor here, they're typically seeing patients, but let's imagine every 2 hours they're called off, or 2 hours on average, they're called off to do something else. They've got to work, do something else on another ward. So they're not available in this system for about an hour. And so we can pull them off with this sort of priority activity here. And we can make this a priority activity, and I'll show you how to do that. So that basically it holds this resource away from all this stuff for an amount of time, and then releases them back. Similarly, you could do the similar thing if you wanted to model them being off shift. So you might have, typically you'll always have some resource if your system is open in some way, but it might be that the amount of resource is reduced. So you might have 4 doctors in the day and 2 overnight or something like that. And so you want to model that 2 of your doctors are not going to be available after a certain amount of time. Okay, so let's come on to sinks, our exit points of the model. So as we said, sinks are the way in which your entities leave the system, or rather the part of the system that you are modeling. That might be where your entity is physically leaving the system, i.e. a discharge from hospital, something like that. But as I said, it doesn't necessarily have to be, and usually it won't be. So it might be that the entity is no longer existing because of they've died, or if it's a test sample, the sample has been used. Or it might be, and this is the most common, the entity is no longer needed to be modeled because it no longer needs access to the activities that we're capturing in our model. So just bear this in mind, that an entity leaving via a sink in your model doesn't necessarily mean they've left the system entirely. It just means they left your scope of the model. So when you're thinking about your perceptual modeling, thinking about the scope, how wide you cast your net in terms of what you capture, they've just left that bit essentially. So as I said before, you might just be modeling the triage aspect of your ED, and so a valid sink might be placed after the triage. They've actually left our model as far as we're concerned. They've finished the triage, but obviously they're still in the ED. Now, of course, in the real world, patients don't linearly flow through processes. It's very rare that you have a truly linear process. And often different things will happen to different entities. And in a discrete event simulation, that basically means that your entities are flowing to different activities or to different sinks. And we might differentiate based on some sort of attribute of the patients of the entity. So for example, you might have an entity that has higher priority value, and then they might flow through a different set of activities because of that. It might be based on chance with some probability. So we might know, for example, that 60% of patients end up being admitted. So we'll randomly select for 60% to be admitted, or randomly select for them to be admitted 60% of the time, I should say. Or it might be we might differentiate based on time. So it might be after a certain time in the day, the entities will flow through a different set of activities. So there's different ways in which we might differentiate and cause different branches to flow down. So here we've got an example where we've got our patients triaged, and then depending on if it's a major incident or a minor injury, they might flow through a different set of processes. And depending on luck and what's happened before, we might say, well, 80% of patients after the second assessment in the major incident path are admitted. So when a patient gets down here, we essentially roll the dice, and there's an 80% chance that they will be admitted, a 5% chance they'll be discharged, a 15% chance they'll die. And so we can use that to emulate the different likelihoods of different branches happening. As with any type of model as well, it's really important to think about what outputs you want your model to generate. And remember, these outputs should mirror and provide you with answers to the questions that you built your model for. in the first place. Now, because discrete event simulation models are typically used to model queuing and resourcing type problems, the usual kinds of outputs that you would have from a discrete event simulation will typically include this kind of stuff here. And usually we take, sort of mean, the minimum, the maximum, the 90th percentile, 95th percentile, 5th percentile, etc., of this sort of stuff. So how long entities were in the system as a whole, how the queue lengths, so how big were the queues getting, and how long were people queuing for particular activities or interests. The rate of resource utilization is often something we want to know, i.e. what percentage of time is a resource being used for. If a nurse is being used 100% of the time, that might seem very efficient, but that means that there is no flexibility in your model. Not least the nurse probably isn't going to like that either, with good reason. And you might also look at the probability of exceeding a defined queue length or a queuing time or a resource utilization threshold. So what's the probability that you're going to exceed a 4-hour wait in your ED, or what's the probability that your waiting room is going to become overcrowded, for example? And the vaccination model that was built by one of our HSMAs last year, that looked exactly that. It would spit out, the model would spit out the probability that they would become overcrowded in the waiting area, which obviously is an issue with COVID. Okay, so that was a bit of a tour through some of the key aspects of discrete event simulations and how these things work and the sort of main components. So I'm going to give you a bit of an exercise to do now, and this is a group exercise. I want you to work in your groups for this. So I've armed you with enough information now to be able to design a discrete event simulation. You're not going to be able to build one yet, because I'll show you that next. But you are going to be able to design one, and that's a really important first step. So what I want you to do is, well, first of all, after I've stopped talking, I want you to take a 5-minute break and stretch your legs, but then come back together in your groups. And I want you to read through the instructions in the file 3AX1 instructions.pdf, which came with the materials for today. And basically this presents you with a fictional problem. Okay, so read through the problem, first of all. And then I want you to do these 3 things. I want you to first draw a process map of the system being described in this here. Now, important note, there is more than one process being described here, so think about how you want to capture that. I want you to write what if questions that capture what has been asked of you as the modeler. So what are the questions that you want your model, if you're building this model, to answer? And then I want you to draw up a design for a discrete event simulation model based on these what if questions that you've drawn out. I want you to indicate what you think the generators are, where the queues are, which activities, which resources, which sinks in the model, and list the entities that you would capture, the inter-arrival times you need to capture, and the activities. By that, I don't mean you don't need to know the times themselves, but what types of inter-arrival times you're going to need to capture, which types of activity times will you need to capture, what will you need data for, that you're going to use. Think about any attributes that your entities might have as they're flowing through this model and how they might be used to determine different branching paths in the model, for example. Think about any queuing policies you might have for each queue, whether you're going to need to capture reneging, bulking, or jockeying, or any combination of those things within this problem. And you should also think about what outputs you'd want your model to generate to answer your modeling questions that you defined in number 2. Do remember and refer back to your notes from the very, very first session 1A, where we talked about scope and level of detail. So you may not need to include everything from the process map of the system in your DES model design. You might choose to, it's up to you, but think about what you're being asked and what your what if questions are, and therefore what from the real world system. So your process map is going to capture, remember, the system as it is now. So that you're capturing everything on that. It's describing exactly what's happening. But then as you move from that to your design for your discrete event simulation, it's probably not going to be a one-to-one mapping. You're probably not going to capture everything from that real world system in your model. So I'm going to give you about an hour and 15-ish to do this. But as they first take a 5-minute break, so we'll resume at about 11:40. So go and stretch your legs, don't think about this for a minute, and then come back, have a read through of these instructions, and have a go in your groups at doing this. Yes, Irma, I've got a raised hand.
Sorry, I have a question which is bothering me, and I'm hoping you can help with it. So, do we model the process map based on the data that we have, or based on talking to users? And you know, what if the process map that the users are describing is not supported by the data? Does that make sense?
Yep. So basically what you would normally do when in the process mapping phase, you would draw your information from your stakeholders. So you would get together a group of people who are involved in this part of the system, involved in the system, probably in different aspects of that system, in different parts, different ways, and you would ask them to basically go through. So if you refer back to your notes from the very first session, we went through process mapping and about how you would do that. You would typically do that rather than looking at the data initially, but obviously then the data might then show something else. And at that point, you might then go back to your stakeholders and say, well, you said this is happening, but we see in the data that this is happening. And that's a very common thing. So we've had, I mean, my colleague Mike could share some stories about people that have said, this will never happen, that patients here will go to that center. That never happens. And then you get the data and see that actually happens quite regularly. So the first step you would then do is that you'd then go back to the stakeholders and say, well, there's the data saying this, so how do we want to go forward? How do we want to design that? But the stakeholders should always lead that. It's their system that you're designing for, but absolutely you should, if you see contradictions in the data, you should be pushing that forward onto the stakeholders. Does that help?
Yes, it does. Thank you.
Any other questions? Sorry. No, great. Okay, in which case, I advise you to say, go and stretch your legs, 5 minutes, and then I'll open up the rooms now, so you can join those whenever you're ready. Get together in your groups, have a read through of that stuff, and then start designing your model. Now, I know some of you using things like Jamboards and all sorts of other things. Use something like that, whatever you prefer. Probably have one person sort of sharing the screen, and then you can all sort of contribute. And I will bounce around in your groups, and I will have a listen in and see what you're designing. And I look forward to seeing this. After you've finished the exercise and we come back at 11:40, make sure you nominate someone, because I will be asking a couple groups just to put forward their designs too. So in case you are chosen, make sure you've got somebody who's your nominated spokesman. Okay, great. Let me stop sharing and I'll open up the groups now. Hi everyone. Okay, welcome back. Hopefully you had a good stab at this. I think I managed to get around to everyone in the end, and saw some fantastic discussions going on how you would design this. Interestingly, so I'll talk about it in a moment. Many of you fell into exactly the trap that I thought you would. That's not a reflection on you. That's just that the exercise has been deliberately designed to be a little bit like that, and it's to get you to learn a fundamental lesson in designing discrete event simulations. But I won't talk about that for a moment, because I want to let you let a couple of you sort of present what you've done, because it's fantastic to see the discussions that were going on. Some really good designs that I was seeing come up, which is the whole purpose of the exercise. So what we'll do, we're gonna let's grab the wheel of names, and let's see which groups are picked. So I'm gonna shuffle this a few times. I'll just make this extra random, and then I'm gonna click spin. looks like it's going to be, yeah, it's going to be Robocop. So, so do we have someone from Robocop who can share, please? If anyone is talking, they're muted. We can't hear anything.
I suppose I can share it. I can see that, Daniel.
Yep, see that all fine. Thank you.
So basically, this was our way of delineating the processes of our model. So we started off with, just seeing what resources are, fundamental, describing the flows throughout the surgery. So the number of GPs we had, the receptionists, the nurses. So we started off with just seeing how the patient sort of accesses to surgery and what resources are required in order to, sort of to get the patient through. So we had a receptionist, but also it's not just about how the patient accesses to surgery, but how long it would take for them to actually get an appointment, for example. So, we've talked a bit about the processes of Renation and balking here. Of course, the patient can get triage straight away, they can get medication, but they can also, sort of access, sort of getting an examination from the GP as well. So it's not just through, getting a prescription straight away. The patient can be triaged, and the queuing policy, is 5-0. So it's not sort of like staged. We've talked a bit about some of the inquiries here. So just some of the additional responsibilities that the receptionist has. So there's obviously additional flows, like, for example, helping the nurses book appointments, about the prescriptions, which we've talked about already, delivering results, and there's some additional administrative time as well. We've described a little bit about the syncs. So there might be no further action at all if the patient has received a prescription from the receptionist already. As well, but one of the important, I'd say, resources, well, what the GP surgery is asking from you would be whether the nurse would, have additional capacity, to lead a smoking consultation clinic, as well as performing so many things, like, for example, doing the triaging, doing the weight loss clinic, and hopefully we've described that through here. So I suppose the main questions which we still need to ask are whether we need a secondary source for the smoking cessation clinic. Do we have additional capacity after modeling everything? I'm not sure if anybody else from my group wants to help chip in.
I think that was good. Thank you, Vit. No, that was that's really good. It's really nice to see that you've considered a lot of the queuing policies as well, and thought where some of that might crop in, and also where some of your you picked up on the point that the nurse in particular and the receptionist are going to be pulled away to do other stuff, and how you might capture that. So yeah, no, really good, really comprehensive sort of description of what's happening in the system, and thinking about the key what if questions there. So no, brilliant, fantastic, thank you very much. Okay, so let's pick on one more group. Let's share the screen again, shuffle that a few more times, and then spin it. Ooh, yeah, no, it's going to be HAL, I think. HAL 9000. Okay, if somebody from HAL would like to share their screen.
Do you want to, Irma? Great.
Hi, sorry about that. Yes, so we've obviously followed a similar pattern, but I think in a slightly simpler way. We've tried to reduce the scope of the model a little bit to keep it manageable. So we did think about the fact that the receptionist is a potential bottleneck and has all sorts of things going on, but we've just got the receptionist feeding in the appointments to the for the testing. We've got people turning up for the existing clinic, but also potentially for the new clinic, and that they're being dealt with on a first in, first out basis. We haven't actually got it on here, but we did think that the queuing policies would probably apply particularly to the 2-hour clinic rather than the testing side of the model. We've got the syncs coming out from the clinic, but also from testing. We've got the sort of 3 generators, the 2 into the clinic, and the 1 is the patients going to the receptionist to book the tests. And the nurse is well, I suppose there's 2 resources. So one question that we wanted to ask is around the occupancy of the clinic over time, but also we would need to look at the kind of capacity for testing over time as well. And these are the other questions that we were thinking of. So percentage of time the nurse is being utilized is ultimately one of the key questions, along with the occupancy of the clinic, in deciding whether a second nurse would be needed.
Fantastic. That looks great. Thank you. And yeah, really good that you've started to think about how you might simplify that down. And actually that sort of touches on what I was hoping you might do in terms of taking that sort of real world complexity and how you might distill that down to answer your questions. So brilliant, thank you, really good. And I love your little process. That's fantastic. So what I'm going to do now, I'm going to show you a solution. It's not the solution, it's just one I came up with, but that will hopefully give you an indication of how you might sort of distill this down. If everyone could just double check they are muted so we don't get any feedback for anyone. And I will share my screen now. One thing I will say is that the kind of slightly deliberate trap in here, the whole exercise has been designed to present you with a very complex problem, in terms of there's a complex system going in here and there's lots of different ways in which people can interact with the various different resources, but actually thinking about how much of that you need to model is actually really important. And one thing that I did notice a lot of the groups did, in fact, the vast majority, is something that we typically see people do for this exercise, is a lot of you were conflating the process map and the conceptual model for your discrete event simulation. So you were kind of doing both at the same time, that you were building out your process map and saying, oh, that's where I'd have an activity, that would be a sync, that would be a generator. Now that's fine, but it does run you into the problem that most of you encountered, where you then start automatically thinking about everything in terms of being a discrete event simulation component, and therefore you start automatically including everything in your model, which is not necessarily the best thing to do, and I would argue not certainly not for this particular problem. So let's bring up the solution. Let me just close that down. Here we go. Right, so this is a solution. It's not necessarily the right answer, and I will obviously share this with you as well. So this was my process map. And this is very separate. So remember, the process map, you're just trying to capture all of the information that the stakeholders are giving you. So in your case, that was the description. Obviously, in real life, you'd have the advantage you could ask questions, but obviously you didn't have that here. You were just only able to go on the information I provided. But you're basically just trying to describe your system. What are they telling you? What are they telling you how this thing works? And capturing everything that they tell you, regardless of whether you think it's relevant at this point. And that's quite an important part of, kind of building the trust, and it's showing you're acknowledging all these complexities that may not be relevant, but it's an important part of the process. So I'm not going to go through all this, but you can see, I've captured the patient calling to see the GP. Receptionist takes those details, and then the GP will triage them, and then they might get some advice, or they might get a prescription, in which case they'll come into reception to collect that, or the interesting bit where they actually need to see a GP, they come in, see them, and then they might just get some advice, or they might get a prescription, or they might need a test, in which case a test will get booked. And then, of course, separate to that, we've got this stuff going on over here, where you've basically got the patients coming in to see the nurse, either for a test, which has been pre-booked, or they're just coming in ad hoc to see the nurse for the weight loss clinic. So that's basically everything you've been told, put down onto paper. Then separately, you then now need to move on to the next step. Say, okay, what am I being asked? What do they want to know about the system? Why do they want the model? What am I going to build the model to answer? And so these are the two what if questions that I came up with. The first is, what would be the impact on nurse utilization and patient waiting times to see the nurse for test and clinic activities if the nurse also ran quit smoking consultations as part of the weight loss clinic? And then the second question, what would be the gain in terms of waiting times and reduced nurse utilization if a second nurse was brought in to run a dedicated separate quit smoking clinic? Because that's a distillation of what you're being asked. They want you to build a model because they basically want to introduce this quit smoking consultation stuff, get the nurse to do it, but they're worried the nurse won't be able to cope because she's already having to do all this other stuff. And so that you're basically building the model to see, well, what if we brought in the quit smoking consultations and had the nurse do them, what would be the impact? And then how much gain would we get if we brought in a second nurse who could just do the stop smoking stuff? So once you've identified those, you're essentially pulled this out from what they've told you. The next step is then thinking, okay, so what in this big nasty process map that has lots of different processes, what do I need to capture in order to answer these two questions? And remember our talk in the first session, always be thinking about scope and level of detail. What is the minimum you can get away with modeling that would sufficiently answer these questions? Okay, and I put it to you that this very simple model is all you actually need in order to answer these questions. Essentially, you've just got 3 generators, you've got 3 activities and 3 sinks. And in this top one here, so you've got 3 sets of activities, 3 pathways, and you've got the same nurse in the first what if question, the same nurse resource that's being used and stretched across all 3 of these activities. Okay, and then obviously for the second what if question, the quit smoking thing, this would be a separate nurse that would be separate and wouldn't be asked to do any of this stuff. And similarly, this nurse that's running the weight loss consultation and the tests wouldn't be asked to do the quit smoking stuff. But this is all you need. You've essentially got people arriving at a certain rate for weight loss consultations. They have that done with the nurse, then they leave. You've got people arriving for quit smoking consultations. They see the nurse and they leave. and you've got tests that have been booked for the GP patients. I saw a lot of you sort of thinking about how you would model the test booking process and the queues and stuff. But actually, you don't need to worry about all of that, because all you need here is a rate at which they are coming in. And so we can just distill all that down, simplify it down to a rate at which patients are going to be seen, an incoming rate in which they're being booked. And then they would perform the test, with the nurse would perform the test, and they would leave. And so you've just got these 3 activities with 3 separate arrival rates. And in the first scenario, the same nurse being used stretched across all 3. And in the second scenario, this one being separated out with a separate nurse resource. And I've indicated there might be, so these queues would be kind of first in, first out, because these are patients that are just arriving for these consultations ad hoc. But you would have this priority of the queues, I would imagine. And again, this is probably where you want to get some more information in reality from the stakeholders, that presumably those who come in for tests would get a priority over those that are just turning up for the consultation. So I've captured that would need to be the case as well. And I've also indicated there may be possible reneging and bulking behavior here for the people arriving for the weight loss consultation and for the quit smoking consultations, where they may turn up and say, they may wait a certain time and think, oh, this wait's too long, I'm going. Or they may turn up and think, I'm not waiting that long, or there's not enough room in the waiting room, or whatever it may be. So capturing that. In terms of inter-arrival times, we're going to need to capture these 3 inter-arrival times: the rate at which they arrive for weight loss consultations, the rate at which they arrive for quit smoking consultations, and the time between GP patient tests. Our 3 entities, I have 3 separate entities here, our weight loss clinic patients, the stop smoking clinic patients, and the test patients. Our activity times for each of these as well. And then probably in terms of output, I'd be looking at grabbing mean, min, max, 95th and 5th percentiles of nurse utilization. I want to know how overrun the nurse is. That's going to be a key thing here. Remember, they're going to ask if they want to know if the nurse can cope. And so if the nurse is being used 95, 100% of the time, the answer is probably no. And also the queue time for each of these queues, and the queue lengths for each of these queues. And it'll give us some sense about not just whether the nurse can cope, but what the waiting times will be in the system. In terms of attributes, the weight loss and smoking clinic patients probably don't need anything, but the test patients, we might capture something about the tests they need, because we might need to determine the distribution for the activity time. It might be that certain tests take longer, for example, and their appointment time, so we can work out their priority. But the key thing here, and as I say, this isn't the only solution, but the key thing that I wanted you to sort of get to was this big complex mass of stuff here that involves all sorts of stuff about the GP triaging the patient over the phone. None of that matters. For what you're being asked, you can ignore all of that. And in fact, all that really matters is this nurse and what they're being asked to do, and capturing the incoming rates of activity for the 3 different things that the nurse is being asked to do. And so you could actually get away with building a very simple model to capture that. And indeed, in this course, you will do exactly that. Any questions about any of that before I move on?
Hi, Dan, I've just got a quick question. I mean, so this is great having kind of a simple model. It does definitely simplify things and make it easier to kind of understand and program. But when your generators are highly dependent on other factors, so for example, the test book for GP patients are in turn dependent on receptionist and a few other factors as well. Do you have to make a sort of decision about how complex the model to make it in terms of getting better accuracy, or do you just try for the simplest model first?
Yeah, good question. So there may be cases where these rates actually, because as you say, it may be highly dependent on another part of the system, that you find you need to model that part of the system. However, I would urge you to think about those very first few questions again, thinking about what's the simplest way in which you can express that. And in fact, unless anything is going to be changed in terms of what's happening in the GP system, which there's no indication that there is any change in this scenario, then actually all you're interested in from all that complex mass of patients phoning GPs and speaking to GPs and getting prescriptions and all of that, the only bit you're interested in is the output in terms of tests being booked. That's the only thing that will affect the nurse for this, and from that part of the system. And so actually, you should be able to distill that down as an output in terms of a rate, a rate, and obviously it'll be a variable rate, but you should be capturing that variability within the distribution. And remember, the key thing and the key trap that people often fall into is thinking that a more complex model is a more accurate model, and that's usually not the case. In fact, usually it's the opposite. Remember, any model, whenever you build a model, you are making assumptions and simplifications, and therefore the more information, the more detail you put into your model, the more wrong you can be, because you're putting in more complications, more activities that you're making more assumptions about, and therefore you're just increasing your capacity to be wrong. So actually having a very simple model like this, where you're saying, okay, well, we need to know the rate at which patients are being booked in for tests, but you should be able to express that without building a model for it, is the best approach usually. Then there may be, it may be that, for example, here in this scenario, if some of the outputs of this model were then feeding back into the way in which patients were coming back in. So in reality, the tests, it might mean that that affects the rate at which people come back in to see the GP, and that could create some sort of loop or something here. Then you might want to consider modeling that. But generally speaking, if you've got a part of the system that is not being changed and that is not of interest to this model, other than the kind of the theoretical output, if you were to build that model, you probably should look at simplifying where you can. Any other questions?
Hello, Dan.
Hi, yeah, go ahead.
Yeah, so from what are you saying is like basically what is asked for, we have to focus on that and then try to just get something like here is the nurse that asks for, do you need two nurse or one nurse? So so we have to just involve that, we have to just add the activities the nurse is doing in that scenario, just that, pick that one, and then concentrate mainly on what the requester asked for. Am I right?
Yes, very much. So your it may be, I mean, so it obviously depends on the context. So it might be that although they're only interested in the nurse, there's stuff going on that you do need to model elsewhere because of the way in which this is either feeding back or because of other complications that you do need to model. But this is, I mean, goes back to the first point I made right at the start of the course, that model design is a bit of an art form. And this is why we ask for sort of creativity and creative thinking in terms of, because actually building the model is pretty straightforward, as hopefully you'll see today. But the design of the model, deciding what bits you need to capture and how you're going to capture them and what bits you're going to exclude and the assumptions you're going to make, that's the tricky bit. And there's no right or wrong answer other than you need to bear in mind those rules, that you're trying to make it as simple as possible so that you can still sufficiently answer your question. And that any additional complexity is going to bring in additional complication and additional wrongness. So that always needs to be in your mind whenever you're thinking about stuff like this. It's probably the hardest bit when people are starting out on the journeys of being a modeler. This is the hardest bit to get your head around, because the natural assumption is that I need to include everything, or I need to include more, because the more I include, the better this model will be. I still remember when I was doing my PhD, which used an agent-based model, and I gave a presentation many years ago, a poster presentation at a conference, and somebody came up and said, oh, that model can't be right, that looks far too simple. And actually, we were able to demonstrate that model was highly accurate, precisely because it was simple. And so don't fall into that trap of thinking that more complexity is a better model. There's something, and we talked about in the first session, there are some scenarios in which you are deliberately building very complex models. You're usually doing that where you're trying to create very accurate predictors of things. But that normally is not the kind of model that you'll be building for this kind of stuff. In operational research, you're typically wanting, you're almost building these disposable models that somebody asks you a question, you're grabbing the information you need, you grab the process map, you understand the system, then you pull out the bits you need, you grab the data for that, you put that in, and you get out the results you need, and then you kind of chuck it away. And that's kind of the way you need to think about designing these kinds of models. Now that's a little bit, when we come on to machine learning, it's almost the opposite. So in machine learning, you cast your net wide. You basically chuck everything, including the kitchen sink, at it first, and then gradually refine it down. But with a model like this, you typically want to start simple and then build complexity in if it's needed, and only if it's needed. Okay, I'll move on in the interest of time, because we're only about 20 minutes before lunch, and I just want to cover a little bit before lunch. So this afternoon, we're going to be looking at SimPy. So you're going to actually practice building a model like this in Python. But to do that, I'm just going to give you some information that you're going to need in order to understand how SimPy works. So let's talk a little bit about SimPy. So SimPy is basically a Python library. It's a very good Python library and very well regarded and well used, that provides a framework for building discrete event simulations. Now, what that means is that we don't have to build, there's nothing stopping you, if you wanted, coding a discrete event simulation from scratch using everything that I've taught you so far and Googling things. That would be absolutely fine. You could create a discrete event simulation from scratch, but you would have to define all of these concepts of what an entity is, what an activity is, what an inter-arrival time is, etc. The benefit of using a framework like SimPy is we don't have to do that. It's already defined these things. So we can talk about entities and activities and inter-arrival times and resources, and it's already done all the hard work for us of defining what those things mean. So we don't have to write that from scratch. Now, SimPy is built around something in Python called a generator function. Now, we haven't talked about generator functions yet, so now I'm going to show you what a generator function is in Python, how they work. So we've talked a lot about conventional functions in Python. You've had lots of practice writing functions, the way we do that is we define a function, and we specify what inputs it'll have, what we want the function to do, and then what outputs usually. And so when that a function like that runs in Python, we call that function by its name, we give it the inputs if it needs inputs, it does its thing, and then it finishes, usually by returning some sort of output. So that's all sort of well understood, and you're used to doing that now. Generator functions are similar, but very different. So a generator function is like a normal function, except it remembers where it was when control is passed back. And the reason it does that is so that when it resumes, it can continue exactly from where it left off. Because of that, they can be used as powerful iterators. Now, an iterator, you've already seen some examples of iterators in Python. It's just we didn't really call them that. Things like for and while loops are other examples of iterators that you have encountered. Something which you sort of iterate through within code. And this is an example of a generator function, is an example of an iterator. Now, this is really, really useful to use when we want a state to be maintained. For example, during a run of a simulation. So let's look at a really simple example of a generator function first. Let's ignore the simulation bit to see how a generator function works and how they differ from a normal function. So let me go over to Spider because it'll be easier to read here. Where's Spider? There it is. I'll zoom in a bit. Okay, so this is an example of a generator function. I define a generator function exactly the same way I define any normal function. I use the def keyword, and then I give it a name and any inputs that I want. This one doesn't have any inputs, but I can put inputs in brackets in exactly the same way. Then I use a colon, and then everything in the code block is then the code that will be run when this function is called. So this function, all it's going to do is first of all going to set a count value to 0, and then I'm going to have an infinite loop here So my while true, remember that creates an infinite loop for us. So just keep doing this. And I'm going to add 1 to the count each time. So it starts off at 0, and then I'm going to add 1. Now the key difference here, so this all looks like anything you'd write in a function. The key difference is this bit here, the yield keyword. Now the yield statement basically identifies this function as a generator function. So yield is like return. So in conventional functions, we use the return keyword to return an output. And that's the point at which control is then passed back to the main program. So we call the function for the main block of code. That function then runs, and then once we use the return keyword to return an output, that's the point at which control passes back. Here, the same thing happens, but we use the yield keyword. That passes control back, but it tells Python this is now a generator function, which means when this function is called again, it'll remember where it was, and it'll start from that point. It won't go back to the beginning as though it's never been called before. Because of that, when we call a generator function, we do it a little bit differently to the way we do it for a normal function. So with a normal function, we give the function's name, and we store the output in a variable. Here, like with object-oriented programming, we create an instance of the function. And it's because what we're doing is we're creating an instance of this generator function, and we can then work with that instance, which means we can have multiple generator functions all running at the same time and at different places. Okay, so here where I say my generator equals keep count generator, that will create a copy, an instance of this generator function. And so I can then work with that copy. And then if I wanted to create another copy of it, I could work with that one separately, and they could be at different points in the function. So to show you how this works, what we'll then do is I'm going to use the print statement, and I'm going to print the results of this generator function. Now, I could have put this in a loop. I'm deliberately, so I'm going to get it to do it 5 times. I could have just put that in a loop, but I've deliberately spelled it out. So I'm just using the print statement 5 times just to show you how this is working. So what we do is we use the next keyword with a generator function, and next basically tells it it can be used for any iterator in Python. It basically tells the thing to unfreeze and move on to the next bit. So every time I call next on the generator function, it'll run until it hits a yield keyword, then it'll stop. And it'll pass control back. And then the next time I call next, it'll carry on from that point. Okay. So in this generator function here, the first time I call it, so I set up the instance and then I call next on it. That will then start it running. It'll start the count set to 0. Then it'll enter this infinite loop. It'll add 1 to the count. So count is now 1, and it'll return 1. Okay. But because we're using the yield keyword, it'll freeze in place. So the first thing it'll do is print the value of 1. When we then call next on it again, unlike a normal function, which would start again back at the beginning and set count back to 0, this will now carry on from where it left off. So it left off here, it'll now go back around the while loop, it'll add 1 to the count, which will now be 2, and it'll return that. Now that function wouldn't work with a conventional function, because with a conventional function, every time you call the function, it would go back to the start and count would be reset to 0. So this is the same function, but written as a conventional function rather than a generator function. We set count to 0, and then we go in an infinite loop where we return 1 and return the count. But every time we call that, it'll go back to here and it'll reset to count to 0. To prove that to you, I will run that code, and you can see what happens here. The first 5 numbers that are printed are 1, 2, 3, 4, and 5. So this is where it's gone round the generator function 5 times. Each time 1 has been added to the count, because it doesn't exit back and start here. It keeps going from where it left off, and it's going around this while loop. Whereas with the conventional function, it's restarting and resetting this count to 0 every time. So the count is always coming back as 1. Okay, so let's go back to the slides. So with a generator function, you're creating an instance of that generator. Process, remember, is called instantiation. We use the next keyword to move the iterator to the next element. That will then set count to 0 the first time it's run, and then it'll enter this infinite loop where it continues indefinitely, incrementing the count by 1, then returning the count and freezing in place. At that point, it comes back out, controls pass back, we print the thing that's been returned, the count. Next then moves the iterator onto the next element, which means it'll then go back, it'll unfreeze and continue from where it left off. And so it'll go back around again and again. So it's exactly like a normal function, except that it freezes in place when control is passed back using the yield keyword. So here we see the instance of the generator function that represents how we might use it in SimPy. So the reason I'm telling you all this about generator functions is because SimPy is built around these things, and this is how we're going to work with them in SimPy. Okay, so basically the broad structure is we have generator functions in SimPy that represent our arrivals, so our discrete event simulator generator. So there's a bit of, you have to be careful you don't get the two confused. There's a generator in discrete event simulation terms, which is what you've been working with so far this morning, which is the way in which entities come into a discrete event simulation. And there are generator functions in Python, which is what we're talking about now. So the way in which we work with this in SimPy is we have generator functions for our discrete event generators. And we also have generator functions that represent various patient journeys. Okay, so let's think about how this would work. So let's just first of all focus on generator functions representing a generator in discrete event simulation. So your arrival of entities. The way we do this is we create an instance of the generator function, which will represent the generator. We start that going, and then these five things will then happen. The first thing that this generator function will do, remember the generator function is representing our DES generator, is it will create an instance of the generator function over here, the one that's going to represent the entity's journey through the system. It'll start that one running, then it'll sample the time to the next entity's arrival, then it'll freeze in place. So we'll sample how long our inter-arrival time is going to be to the next patient. We'll freeze in place using a yield until that time has elapsed. And then when that time has elapsed, we can then continue in this generator function from where we left off. So we then unfreeze and it goes back to 1 and it creates another new journey representing another patient that's come in, starts that one running, then it samples the time to the next patient and then freezes in place and it goes back round and round and round. So each time it's basically setting up a new patient journey. It starts that generator function running, then it samples how long it has to wait, then it freezes in place until that time's elapsed, and then it goes back around and keeps doing that. And because it's a generator function, it continues from the point at which it left off. And because it's a generator function, we can have separate instances of this generator function, one for each DES generator we have. So if we've got 3 ways in which patients come into our system, we can have 3 separate generator functions, all generating those different ways in which they're coming into the system. Separate to that, we also have for each type of journey that we've got, we also have a generator function to represent that. So these are the things that are being kicked off in the generator function that's representing our DES generator. So the DES generator is basically saying there's a new patient that's come into the system, start one of these running, which will describe their journey, which is in itself another generator function. So what this will do is each time one of these is started off, it'll grab the time that the patient started queuing for activity 1. It'll request the required resources it needs for that activity. It'll then freeze in place until those resources are available. So that's the point at which it will freeze. When those resources are available, it will then resume from where it left off because it's a generator function. It'll grab the time that it finished queuing, the patient finished queuing for this activity, so it can calculate the queuing time. It'll then sample the activity time from a distribution, so how long the patient is going to spend in this activity. It will then freeze in place again, holding the resources that it needs with it too, for however long it's sampled. And then once it's unfrozen, that activity is finished, it'll move to the next activity and go back and do all this again. So this, I appreciate this probably sounds a bit complex. I'm going to keep showing you how this works in practice, and you will get the hang of this. But basically, you've got generator functions. So let's just imagine, for simplicity, you've just got one generator in a way, one way in which patients come into your model, and one type of patient journey. So the generator function that's representing patients coming into your model is basically going to create these patient journeys. It'll set these things off and running, and then it'll freeze in place until the next one's ready to, the next patient's ready to come in. And then at that point, it'll create the next one, setting off running. Meanwhile, all of these generator functions that are representing these patient journeys, these individual patient journeys, are going to be basically calculating the time that they started queuing, then requesting the resources, then freezing in place until that resource is available. Then they can calculate how long they were waiting. It'll then sample how long they should spend in this activity. Then it'll freeze in place again whilst that activity happens, and then they'll move on to the next activity if there are any more. Sorry, yes, I did see a raised hand.
Hi, I just wanted to understand, when we say sample the time, are we giving it random inputs? Are we asking it to run random inputs, or are we feeding data in to the generator?
No, so you're randomly sampling from a distribution. So this is what we were talking about before, that you use typically use an exponential distribution to sample your the time to the next entity arriving, so your inter-arrival time, and for your activity times, you're sampling either usually from an exponential distribution or from a log normal distribution. So you're randomly sampling from a distribution for both of these things. Very rarely would you have fixed time. Sometimes you would, but very rarely.
And I guess we just set the parameters to that to match the reality.
Yes, that's right. So you would, if your average inter-arrival time is 5 minutes, then you'd set up an exponential distribution that had a mean of 5 minutes.
Oh, okay. Oh,
yeah. So you're going to practice doing all this anyway, and it'll make much more sense.
Thank you.
Okay, so I think the only thing to say on that is that so I gave one example, but you can have a generator. Essentially what your generator is doing is it's creating all these instances of these other generator functions that are representing your patient's journey. Okay, so here's my generator. This is, imagine patients arriving by ambulance. First patient arrives, create an instance of this generator function, which will describe their journey through the system. 10 minutes elapse, another patient arrives by ambulance. Now create this separate generator function, which will describe this patient's journey through the system. And they're all going to be at different points. Okay. So this is your DES generator that you've been using this morning, your entry points to your DES model. And these represent your individual entity journeys. And these are your inter-arrival times, the times between these things being generated. Okay, this will make more sense, I promise you, as you come to do this, but I'm just before lunch, I'm just going to quickly show you what this looks like in SimPy and how you do it. And I'm going to use this really simple example that we looked at this morning. Okay. So all I'm doing is I'm taking this one bit from our model this morning, where we've got patients coming in for a weight loss consultation. They wait to see the nurse and then they leave. Okay, so we've got a generator that is generating people arriving for a weight loss consultation. They queue, they wait to see the nurse for this consultation, they spend an amount of time with the nurse, and then they leave. Really simple model. Okay, that's all we're capturing in this bit. And I'm going to show you how to write exactly this in SimPy. Okay, so here we go. Go back to Spider. Now, most of this code here is actually comments. If I were to take the comments out, you would see how few lines of code you actually need in order to do this. But obviously, I want to try and explain this as much as possible. So the first thing we do, as with any package in Python, is we import the packages we need. So we need to import SimPy. And I'm also going to import random because I want to randomly sample from distributions. Okay, so you've used random before. Obviously, you haven't used SimPy before. So if you haven't installed SimPy, you need to make sure you pip install SimPy for this afternoon. But as long as that's been pip installed, you'll be able to import that. If you haven't done that, it'll tell you that there's no such package called SimPy, and that's the point at which you would then need to install it. So here, this first function is this is a generator function that is going to represent our patient generator, i.e. the generator that is bringing new patients into the model. Okay, so what this function is going to do is going to create the new patients that are arriving into the weight loss clinic. Now what we do, I've given it a name, I've called it patient generator weight loss. And I need to pass it certain things. So I'm going to pass it this, which is env, which represents the simulation environment. This is the a SimPy thing. You have a simulation environment in which all of your stuff lives, and that's the thing you pass it here. We'll come on to that in more detail later. I'm also going to pass it the mean inter-arrival time, because I'm going to need that to feed into my distribution so I can sample from a exponential distribution when the next patient should come in. I'm going to pass in the mean consultation time, so on average, how long is a patient spending with the nurse? And I'm also going to pass in the nurse itself, so that this is the nurse as a resource. And again, remember I said SimPy already knows what a resource is. This, which we'll set up, I'll show you in a moment, we set this up as a SimPy resource, and it knows this is a resource thing. So in this generator function, what I'm going to do, I'm going to set up and create just a patient ID. I've just got a simple counter here, just that each patient has got their own ID so I can track them. And then I'm going to go into this infinite loop, which basically just keeps telling Python to do this indefinitely whilst the program is running. Okay, now you'll see in SimPy, you can tell SimPy how many time units you want the simulation to run for. So it'll keep doing this while the simulation is running. And the stuff we want it to keep doing, the first thing we do is we create an instance of our activity generator, which I'm going to show you in a moment, is this thing down here. That's the thing that's going to represent the patient's journey, which is a fairly simple journey. They just wait to see the nurse, and they see the nurse and then they go. But it's this is their journey generator. So we create one of those. I'm going to need to pass in the things that generator will need, which will be the simulation environment, the mean consultation time, the nurse, and I'm also going to pass in the patient ID, which I've set up here. I don't need to pass over the inter-arrival time because that's only needed in here where we're creating new patients. We don't need it after that. So I don't need to pass that across. I just need to pass across the rest. So once I've created an instance of it, I need to tell tell SimPy to kick off this this generator function. And the way we do it in SimPy is we tell the environment to process this generator function. So I've called my generator function WP here. So I tell it to process that. So I've created an instance of it here. Then I tell SimPy to basically start it running, start that patient's journey running. Once I've done that, I am in here, I am the generator function that's representing new arrivals. So the next thing I need to do is to randomly sample the time until the next patient comes in, which I've got my mean here. I'm going to sample with an exponential distribution. Remember, with an exponential distribution with the expovariate function, we specify it as lambda, which is 1 over the mean. So that's why I've put in 1 over the mean here. So I sample that time, so it's 6 minutes or whatever it may be. And then I use the yield keyword and I call a timeout using the SimPy environment. We say env.timeout, and then we pass in that time. And what this does is it tells SimPy freeze in place until that time has elapsed in the simulation. Okay, so that will then freeze, and this generator function won't do anything until that time has elapsed in the simulation. When that time has elapsed, because it's a generator function, it'll restart from this point. So when that time has elapsed, all I'm going to then do is increment the patient ID, which started at 0, ready for the next patient. So that'll be patient 1 now, and I go back around again. I create another generator function for my the next patient journey. I tell SimPy to process it, to start kicking it off running. then I sample the time to the next patient, I freeze for that amount of time, and then I wait, and then when that time's elapsed, I then set the patient ID for the next patient. That's all I'm doing each time. So down here, this is the generator function that describes the patient journey, i.e. the one that I'm kicking off each time in this generator function up here. And so remember, the things I need to pass into that are the environment, the average consultation time, the nurse as a resource, and the patient's ID. And then all I'm doing here, I can use env.now to basically say, what's the current simulation time now? And I can do that so that I can calculate how long they were queuing for. So I can store that in a time entered queue for nurse. And I store that as in this variable. And I'm just going to print a little message here saying they joined the queue at this time. Then the next, so we start off, they're queuing, they're waiting for a nurse. And the next thing I need to do is I need to request a nurse, okay? And the way we do that is using the with statement. Now, remember when we talked in the very first session, or was it the second one? I think it might be the second one, Python session, about the with statement. And we talked about it in terms of holding open a file while we did some stuff, and then it let the file go, it closed the file again. Same principle here. We use the with statement to say, basically, when a nurse is available, grab that nurse and then do all of this with the nurse in hand. As soon as you finish that, you can let the nurse go. But until this has been finished, the nurse is held in place. I need you to do all of this with the nurse. And we do this by calling the request function on the nurse resource. Remember, we called our resource nurse. We call the request function. I refer to it as rec during the rest of this function. So the first thing we do is we call the yield command here to return the request. Basically, what this is doing is it tells the function to freeze in place until a nurse is available. So SimPy says, okay, I won't do anything until a nurse is now available. SimPy is doing all the management of this for you. Once a nurse is available, it will then resume from this point. We can now calculate what the time is now, and then that will allow us to calculate the difference between the time now and the time when they first joined, and that will be the queuing time, which is a really nice, easy way for us to get the queuing time out. So now a nurse is available. We've got a nurse, and we're doing all of this. The nurse is being held hostage with the patient. They're both being held together. So I'm going to sample my consultation time. How long am I going to spend with the nurse? Again, I'm just doing it with an exponential distribution here. So I put in 1 over the mean that I passed in. I then tell the function again to freeze in place until that time has elapsed. So if I sample that the nurse is going to spend 20 minutes with this patient, then for 20 minutes of simulated time, that nurse and this patient are locked in and nothing happens. They're just frozen together. Okay. Once that time elapses, the patient has now finished with the nurse. Then I'm just going to print a little message here saying the patient's finished at whatever the time happens to be now. Okay. So, and that's all I need to do. So in this case, that's the end of their journey, because remember, all we're modeling here is a patient coming in, waiting to see the nurse, and then they see the nurse and they leave. If we had another activity after that, that's the point at which they would then go on to the next activity outside of this with block. And you'll see an example of that this afternoon. So those are our two generator functions. They're controlling the model. We've got one that's controlling the generation of new patient journeys, and one that's describing each patient's journey and what needs to happen. Okay. So down here, remember, as with any functions in Python, we define them. That doesn't set them off running. So we need to do everything and actually call them and use them. So in here, the first thing we need to do with SimPy is we set up a new SimPy environment. This line of code you will just use pretty much every time. You say env equals simpy.environment, just means create a new SimPy environment and call it env. That's the standard convention. Then I'm going to create my resources. I've only got one resource here, one type of resource called a nurse. And I say that nurse is a simpy.resource, so it knows what a resource is already. And the things I pass into that are the environment, the SimPy environment in which the nurse will live, which is I've already created up here. and I pass in an argument that says capacity, which tells me, tells SimPy how many nurses I have. So in this case, I've just got one, but that means I can very easily add in another nurse just by doing that. I can change that immediately. So I've set up my environment, I've set up my resources, which I've only got one here. Then I'm going to set up my parameter values that I'm going to pass in. So all I've got for this simple model is my mean inter-arrival time, which is going to be 5 time units. I assume they represent minutes, and mean consultation time of 6 time units. So I've set up my environment, I've set up my resources, and I've set up my parameter values. All I now need to do is start up the patient generator function, that top one, because this is the one that's going to kick everything off, because that one will then, by starting that up, it'll start generating new patient journeys. It'll start creating the second generator function and start those running. So I'm going to set that one off using env.process. Remember, that's how we set off a generator function using SimPy. And I'm going to pass into that the name of the generator function, which is the patient generator weight loss function. And I'll pass in the things that it needs, which, remember, are the environment, the inter-arrival time, the mean consultation time, and the nurse. All of that I've set up here. And then the last thing I'm going to do is just tell SimPy, off you go then, run. And I can do that just by saying env.run. And then I put in brackets here until equals 120, means basically run for 120 time units. Okay, so all I'm doing is creating the environment, creating my resources, creating my parameter values, passing all of that into the generator function that represents my discrete event simulation generator. If you have more than one, so if you've got multiple generators, different ways in which patients are coming in, you'd set them all off and running here. And then I tell SimPy to run from a certain amount of time. So this is minutes, 2 hours of simulated time. Let's run that very quickly. Push F5. There we go. It's run. It's finished. And if I scroll up through here, you can see what happens. So patient 0 joined the queue at 0. It left the queue at 0 because there was no queue. They were the first patient in. So they queued for 0 minutes. They finished with the nurse at time 1. Then patient 1 joined the queue at time 2. They didn't queue for any time because there was the previous patient had finished. And so then they queued for 0 minutes. But patient 2, meanwhile, comes in at time 4.2. Patient 1, the second patient, finishes at 11.5. So patient 2 is waiting. They have to wait from 4.2 to 11.5. So they waited for 7.3 minutes. Then they finish with the nurse at 11.9, and so on and so on. Okay, and you can see that gradually a little bit of a queue starts to build, where some of the later patients are starting to queue for a little bit longer, which is what we'd expect. Okay, right. I'm going to stop talking now because I'm conscious it's time for lunch. So we'll resume again at 1:30. Just switch off your mind from it for a bit. Don't worry, this will all sink in, and we will go over this, and you will have practice doing this. But this is basically how it works. You set up a generator function to describe new patients coming in, a generator function to describe their journeys, and then you set it all off and running. And that's basically all you do. It's actually really simple once you get used to it, because you use the same template for whatever you do. Okay, but go and have some lunch now. Stay on the call, just mute yourselves, and you can resume at 1:30. And this afternoon, I'm going to show you how to build this, and you're going to get some practice building these models. Okay, I will stop sharing now and go and have lunch, and see you in 50 minutes. Okay, good afternoon, everyone, and welcome back. Hope you managed to stretch your legs and get some sustenance over lunch, and back to SimPy, which obviously we started talking about at the end of this morning's session. So as I mentioned, this will take a little bit of getting your head around, so don't worry if you're not fully following it at the moment. I promise you it will slot into place the more you do this, and you're going to get lots of practice this afternoon being able to build models in SimPy. Also, just a matter of sort of housekeeping, apologies if I have to suddenly jump off and answer the door. Unfortunately, I'm home alone at the moment, and I'm expecting delivery in the next 30 minutes. So it's possible I may have to just jump and answer the door. So apologies in advance if I have to quickly do that. I will be back, I promise. So just a little sort of message, really. So there are two sessions that you're going to have on SimPy. This is the first one. And then there's going to be another one in a few weeks' time. Everything that I show you this afternoon will be enough for you to build a discrete event simulation model in SimPy, and you can go away and happily do that using everything that you learn today. But there are two principal ways in which you can build SimPy models. One is the way I'm showing you today. And then there's also an object-oriented approach, which is the favored approach. And for reasons that will become clear, is actually a much neater way of building your models, particularly when you go to do anything more than a trivial model, as we mentioned with the object-oriented training last week. But the reason I'm showing you this way first is because this will expose you to all of the generator function stuff, which is at the heart of SimPy. And so if you can get your head around doing it this way, you'll then see the benefits of doing it using the object-oriented approach, and being able to have sort of patients or entities that are holding their own attributes and things like that. So you'll be able to see where the benefits come in, and you'll be able to understand a lot more how to do the object-oriented approach. But if you are interested in doing a discrete event simulation model, I would recommend that you come along to that second one in a few weeks' time, where I'll basically show you how to do all of this, but in an object-oriented framework. But just to say, everything I'm showing you today will allow you to build a discrete event simulation model using SimPy. So before I sort of go on to, I'm just going to very quickly switch back to Spider, and I'm just going to go back to this version. This is exactly the same code that I showed you before, but with all of the extensive comments trimmed down. I'm just going to very briefly go over it one more time, just so that you can get your head around this, because this is the fundamental way in which you build a SimPy model. So if you can get the hang of this, everything else is really easy. Okay, so I'm importing SimPy and importing random here because I'm going to use SimPy, and I need the random library to sample from distributions. I'm going to set up two generator functions, one for my discrete event simulation generator, which will generate my new patient arrivals, and one here for my to describe my patient journeys as patients go through and see the nurse for the weight loss clinic. So in my patient generator here, where I'm generating new patients, I pass in the SimPy environment. I pass in basically the stuff I need. So I need my inter-arrival times, because I'll need to know that in here. I'll need the mean consultation time, which I'll need to in turn pass on to the other generator function. And I'll need my nurse, which is my resource, which again, in turn, I'll need to pass that on to the other generator function. And then basically, I'm going to keep going through this infinite loop indefinitely, or rather until SimPy stops the simulation. And basically what I'm going to do each time, I'm going to create a new instance of the activity generator. That's the thing that's going to describe the patient journey, pass across the things it needs. I'm going to tell SimPy to kick this off running using env.process, and I pass in the instance of the generator function I just created. Then I sample a time until the next patient randomly. I'm going to sample for an exponential distribution here. And then I'll freeze this function in place until that time has elapsed. And then when it's time to generate another patient, I'll increment the patient ID by 1 and I'll go back round again. So basically, create a new patient journey, start off that journey, work out how long I'm going to freeze in place to the next patient, and then freeze. And that's basically what you're doing each and every time. Creating a new generator function, setting them off, freeze, and then sample the time until you freeze, until you can wake up again, and then freeze. Those 4 steps is basically all you're doing. And then the generator function here that I've got, which is describing the patient journey. So I'm passing across the environment, the mean consultation time, which I'll need to know to sample how long I'm going to spend with the nurse itself, and also the patient ID. And I'm going to record the time they started waiting for the nurse, which is now when this kicks off will be the point at which the patient enters the model. So we'll record the time now. I'll print a little message. Then I'll request a nurse. So basically the patient says, I want a nurse. And it will wait in place, it will freeze in place until that request can be met. As soon as that request can be met, this generator function will unfreeze. It'll then check what the time is now. Obviously, if there was no wait, then the time will be exactly the same. And then we can calculate the time they spent queuing. Then I'm going to sample how long I'm going to spend with the nurse from, again, I'm going to do it for an exponential distribution here just for simplicity. And then I'll freeze in place until that time has passed with the nurse as well. So patient and nurse are frozen in time for that amount of time until they are then both released. And that's basically my model. That's all I need to do. And then all the stuff down here is just the setup. So I set up my SimPy environment. I set up my resources, which is just a nurse here, of which I've got 1. I set up my parameter values, which will be my inter-arrival times, my activity times. I start up my arrivals generator because that thing's going to kick off everything else. And then I tell SimPy to run. And I'm going to tell it how long to run. And I want it to run for 120 time units. Now, remember, with time units, SimPy just treats them as time units, so they can represent whatever you like, but you need to be consistent. So you need to be very clear about what your time units represent. So in this case, my time units are going to represent minutes. I don't need to tell SimPy that, but I need to make sure that, therefore, when I'm putting in my mean inter-arrival times and stuff, that represents the time unit I'm using. So 5 minutes for inter-arrival time, 6 minutes for my mean consultation. Now, obviously, we can see with this model here, patients are arriving very slightly more frequently than they can be seen by the nurse on average. So patients are arriving every 5 minutes on average, but they're taking on average 6 minutes to be seen by the nurse. So you would expect over time a queue to gradually build. It probably won't be much. And in some cases, we might have a run of good luck and it's absolutely fine because it's random, remember. But we would expect there to be a little bit of a queue brewing. And in fact, we can start to see that if I run that again. Generally, the later patients starting to see queues, whereas the earlier patients aren't, which is what we'd expect. And obviously, the longer that would run, we'd see more of that effect. So that's just what we went over before lunch, and that's basically the core of what we do in a SimPy model, using a very simple model. This is just a simple single activity, single resource model. Okay. So obviously, in reality, we probably have more than one activity, at least in our system. Let's first of all just consider the simplest way in which we could have more than one activity, i.e. a simple linear system, where patients basically queue for one activity, and then once that's done, they queue for another activity. Okay, so really simple. So here I've got the system that I'm going to model. I've got patients arriving at an ED. That's my generator. They queue to be registered here, and that needs a receptionist. And then once that's done, they queue to be triaged, and that needs a nurse, and then they leave. Okay, so really simple system again. It's just this time, rather than one activity, they've got 2, and they do one after the other. Okay, and they just do them sequentially. So really simple. So let's see how we would do that in SimPy. So if I flip over here, so again, same with my imports here, exactly the same as before. I've got my arrivals generator function, the same as before. So I've called mine here patient generator ED. I pass in the environment. I pass in my inter-arrival time. I'm going to pass in 2 lots of mean activity times. So I've got a activity time for registration and also activity time for triage. So I need to pass both of those in because they'll both need to be passed over in turn. And I've got two resources this time. I've got a receptionist and a nurse. And so I'll pass both of those resources across. I'm going to set a patient ID again. I mean, in reality, you depends on your context. You may or may not do this, but it's quite handy for tracking individual patients in your model. And then I'm going to set up my infinite loop, where I'm going to create a new patient journey. I've called it P here, which will be an instance of the activity generator function below. So I'll pass across to that the environment, the activity times, and the resources and the patient ID. I don't need to pass across the inter-arrival time because we don't need that after the split. It's only in here we need that. Then I'll use env.process to start that activity generator running. I'll sample my time to the next arrival, and then I'll freeze in place until that time's elapsed, and then I'll increment the patient ID and go back around again. So that's all pretty much as it was before. It's just we're passing in a couple of extra things because we need more. We've got more activities and more resources. Then in my generator function, again, I set it up in exactly the same way as before. I've called mine activity generator ED here. And the first thing I do, again, I'm just going to capture the time that it is now. I'm not going to print a message this time. I'm just going to capture the time that they entered the queue. And then remember, now we've got two queues. So I'm going to say time enter queue for registration. Then I'm going to request a receptionist. So I use the .request method on the resource, which I've called receptionist. And within the with statement, I say, and I need all of this to be done whilst you've got the receptionist hold. Okay, so the first thing to do is freeze in place until that request can be met. Then I'll calculate the time at which they left, and so that allows me to calculate the total time they were queuing. I'll print a message. Excuse me. Then I'll sample the time that they're going to spend in registration in this activity. So I can use the mean register variable that I passed in, and then I'll freeze in place until that time's elapsed. So exactly the same as before, exactly the same principle. Grab the demand the resource, freeze until you can have it, and then as soon as you've got it, grab it, hold on to it, record the time you left the queue, calculate how long you were queuing, then calculate how long you're going to spend with this receptionist, this resource, and then freeze in place. Okay, so exactly the same as before. The only difference this time is that now, after they've registered with the receptionist, they're going to do a second thing. We want them to go on to the next activity where they're triaged by the nurse. Apologies if you hear that my cat has decided to start sniffing my microphone. So all we need to do, and it's really easy, is we just go back outside of, so we're outside of the with statement here because we're unindented again. So all of this will be back outside. The receptionist has been let go. They've been freed. So now we just say, this is what I want you to do now. And it's basically the same thing again. This time I'm going to record what time it is now, because now I'm starting to queue for triage. Then I'll request a nurse, and then I'll freeze in place until that request can be met. And then I'll do all of this with the nurse, which is I'll record the time that they, when we've got to this point, the nurse is available, therefore that I've stopped queuing. I'll calculate the time that I spent queuing. I'll print that. Then I'll sample the time I'll spend with the nurse, and then I'll freeze in place. So I'm doing exactly the same as I did before, except this time I'm doing it with the nurse instead of the receptionist. So you've literally just got one activity. You hold on to that resource. When you finish with that, record the time you started queuing for the next one, and then do the same thing again. That's all there is to it. And you can see, hopefully you're starting to see that although this might be a bit weird to get your head around, once you get your head around the basics, it's really easy to put these models together. If I wanted a third activity, I'd just do another one down below. Really straightforward, okay? And then all the stuff down the bottom, same as before. I set up my SimPy environment. I set up my resources. This time I've got two different resources. So I've got a receptionist and a nurse, and I'm going to have two nurses just for fun here. So I've set my capacity to 2, but I've got 1 receptionist. Set up my parameter values, which are my inter-arrival time, and I've got 2 activity times this time. I start my arrivals generator, and then I tell SimPy to run. And this time I've got it running for 2 days, if this represents minutes. So 2,880 minutes, that's 2 days worth. You'll get to know that there's 40 minutes in a day when you're modeling, because you'll very often be modeling in minutes, and therefore you'll get to soon know that. So that's all there is to it. Okay, so that is now a really simple model of that second system. If I run that, I can see this is obviously run for a longer period of time, so run it for 2 days, and we get all this information here about when they started queuing for registration, when they started queuing for triage, etc. Okay, so straightforward so far. Let's now go back. So obviously that's a simple linear system, but obviously as we've discussed this morning, in real world systems, not everything is linear, and very often you'll have branching paths that will come up in your systems. So for example, in the system we've just looked at, after they've been triaged, the patient might be referred to an ambulatory care unit to diagnose and treat the patient, or they might get an assessment in ED. And so there'll be two different things that could potentially happen to that patient. And let's imagine that, say 80% of patients get assessed in the ED, but 20% of them go off down this branch and get assessed in the ACU. So you might think, well, how are we going to do this? But actually, this is the beauty of using something in Python, because we can just use Python. You already know how to do this. You may not recognize it yet, but you do. All you need to do for something like this is just conditional logic. You're just saying, if this, then do this, otherwise do that. That's all you need to do. And that's the beauty of coding in something like Python, and using a Python-based framework, is that you can just use Python constructs to do all this. So let's have a look at how we would do this in Python. So here, I won't go through all this again because this is exactly the same as it was before. My generator function is identical, except for I'm now having to pass through quite a bit more stuff because I've got more activities. So it's just one into arrival time still, but I've now got 4 potential activities. We don't know which branch they're going to go down yet. So I have to pass them all across, and I've got 4 potential resources. Now, you're probably already starting to see that this can get quite messy if you've got quite a big system, and you're absolutely right, it can. And when you come along to the object-oriented session of SimPy, you'll see why the object-oriented approach is so much better, because you don't have to do all this. Okay, so if nothing else demonstrates why the object-oriented approach is better when you've got anything beyond a trivial model, it's the fact you don't have to remember to keep passing all this stuff around all the time. You're passing in your inter-arrival times, all of your activity times, all of the resources, you're passing them from one place to another all the time. If you don't use the object-oriented framework, that's what you have to do. Okay. So, but other than that, everything's exactly the same as before. Obviously, the activity generators can be passed this extra stuff as well, but that's all as it was before. So then my generator function, all of this is identical. So seeing the receptionist exactly as it was before. Then I go and see the nurse for my triage. That's all exactly the same as it was before. No change there at all. This is the bit where it changes, because this is now where we've got the branching path. So after they've been triaged, I'm just sorry, I think that might be the delivery driver. Yes, it is. Apologies, I shall be 2 seconds. Hi everyone, sorry about that. Right, at least that's done now. I don't have to constantly have my eye out the window. Right, so where were we? So this is the point, yeah, that we're going to branch off after the patient has been triaged. And so this is the point at which we basically going to decide whether the patient goes to ED or stays in ED rather, or whether they go to the ACU. And we said that 80% of them will stay in ED, but 20% of them will go off down the ACU branch. So we said that we can just do this really easily using conditional logic. And you already had a bit of practice doing this in one of the recent sessions. Remember, we used the random uniform distribution to generate a number at random between 0 and 1. And then we can compare that against a simple probability to determine whether they go down one branch or another. So if we generate a random number between 0 and 1, then and we check whether it's less than 0.2, for example, then we know that there's a 20% probability that a randomly chosen number between 0 and 1 using a uniform distribution, where everything's equally likely to be selected, the probability of picking a number less than 0.2 is 20%. And so that emulates our probability of going off to the ACU. So if you randomly pick a number between 0 and 1, it's less than 0.2, then you're earmarked for the ACU. And so all we need to do is just put in an if statement and check that, randomly generate our number here. If it's less than 0.2, then do this. And all I'm doing here is exactly as I did up the top. I'm doing exactly the same process, only this one is requesting an ACU doctor and queuing for the ACU, and it waits in place and calculates how long it was waiting, calculates how long it's going to spend with the ACU doctor, all exactly the same as before. If we decide not to go down the ACU, if the number is 0.2 or more, then there's an 80% chance that means that we're staying in the ED, and so we go down the else branch. And so we do exactly the same here. It's just this time we're going to be using the ED doctor. So exactly the same principle. We're just using an if-then statement to work out basically which route we're going to go down. And everything else is identical to as before. We've got more stuff. We've got more resources this time because we've got all this extra stuff that we put in the ED doctor and the ACU doctor. We've got more parameter values and all that, but exactly the same principle. Set up your environment, set up your resources, set up your parameter values, start the arrivals generator, and then run it for a certain amount of time. So I run that, you can see that it generates the various results, and we can see here there's some pretty big queues building in ED assessment. They're starting to wait for 619 minutes here by the end, so there's big things going on around there, although the ACU assessment looks even worse. And actually, if we look at some of these numbers, we can probably see why, because some of these numbers will look familiar. If you remember back to the very first session where I got you to build or look at a little simple ED system, theoretical ED system, and I said patients arrive every 8 minutes, so it takes 2 minutes to be registered, and then it takes them 5 minutes to be triaged, and then 30 minutes to be assessed, etc. Exactly the same system that we're building here, and we can see the potential disaster of that system here. Okay, so that's all there is to it. So you've got a simple a linear model where you just put things one after the other, or you can have branching paths just by using conditional logic. That's all you need to do for that. Okay, so those are the basic building blocks, and you can build. If I were to stop there, you could go off and quite merrily be able to build some models now. And be able to do this. In fact, you will in a moment. But just one last little thing before there's some extra fancy stuff that I'm going to be showing you in this course as well, and really useful stuff that you probably want when you're doing this in practice. But if you can get those basics, then you can build a discrete event simulation model using SimPy. It really is as simple as that. And so you get your head around those sort of fundamental basics, and that's all you need to do each time. But just one more thing before I get you to have a little go at this yourselves. So let's imagine that we want to store the results of our simulation run. So for example, we can calculate the average queuing time across patients. That's a pretty common thing that you'd want to do because you, as we discussed this morning, you'll very often want to look at average queuing times in a system. So one way we could do that would be to set up a list which stores the results we're interested in, and then adds each patient's results to the list. Now, to do that, using this framework, using the non-object oriented framework, we need to make use of something called the global keyword, which I'm going to introduce you to now. Now, this is another reason why in practice, it's good to use the object-oriented framework, because you don't need to do this. This is a little bit, well, it's not dodgy. It's perfectly fine. It's actually very, it's perfectly valid Python code, but it's not the preferred way of doing things. But nonetheless, I will show you, because this is the way you will need to do it if you're using a non-object-oriented approach. So let me flip back to Spider. Okay, so this is exactly the same model I had before in the last one, where I've got patients coming in. They no, it's not. It's a completely different one. What's this one? Okay, so this is where they're coming in and they're just being seen by a nurse. We've gone back to the very simple one. Okay, so I've got my imports up here as before, SimPy and random, but I've also got this extra little import that I make, which I didn't tell you about before when I was getting you to manually calculate means for all those exercises, which is probably a bit mean of me itself, but there is actually a nice little mean package in the statistics library. If you import mean from statistics, you can really easily take a mean of a list. Just to shut the door because my cat's loud. Yeah, so that's a really handy little way in which we can easily take a mean of a list, which is something common you'll want to do, particularly when you're modeling. So I've got my arrivals generator function, as I did for that very simple model here, where I'm just passing in the environment, the inter-arrival time, and the mean consultation time and the nurse. Then I go through my steps of setting up a new activity generator, setting that going, randomly sampling the time to the next patient, and then waiting and freezing in place until that happens. So then in my activity generator function, this is where I'm going to want to, so before we were calculating and then basically just printing out how long a patient was waiting in each time. But that's probably not the best thing to do. I mean, that's great for testing, but obviously if you gave that to someone and said, there you go, that will tell you, and then made them sort of scroll through reams of messages trying to work out how long patients are waiting, it's not particularly useful. So in reality, what you'd want to do is to look at the average results over a run, for example. So what we're going to do here is use what's known as the global keyword. Now, remember I said that each of these activity generators, there'll be one for each patient that comes in, and there'll be separate instantiations, separate instances, and they're all at different points because they represent different patient journeys. That means that each of these things, whenever we calculate a patient's waiting time, their queuing time, we need to add that to a list that's outside of that generator function. Otherwise, it's just going to be unique to that patient. What we want is to say this patient waited for this amount of time and sort of call that out to something else that's centrally holding and looking at all of the patients that are coming through. Now, in the object-oriented approach, as you'll see in the follow-up session, that's really easy to do. You have basically a separate class that stores that. But here we need to do things a little bit more, a little bit differently. Now, you'll also remember that when I introduced you to functions back a couple of weeks ago, I said that any variables that are declared within a function body only exist in the eyes of Python inside that function. So anything that you refer to within a function only exists in that function. It doesn't exist outside. And obviously that's an issue here because we want to refer to something outside. Okay, now we could of course save it to file, and that's an option, and I'll show you how to do that as well. And in reality, you probably want to be doing that, although you probably don't want to be doing that for every patient that comes in all the time. You want to grab, at certain time stamps, sort of grab out a list. So if we want to put this into a global list, something that's outside of this function, we use the keyword here, global. And by putting the word global in front of a variable name, what this tells Python is, when I say list of queuing times nursed here, I'm not referring to a name of a variable in here. I'm referring to a name of a variable outside of the function. So it will then look for something called list of queuing times nurse, which you'll see in a minute. I've set up down here, and it'll say that's the one I mean. I don't mean anything in here. By using the global keyword, I'm saying there's something outside this function called this. That's the one I'm talking about. Now, you can get away without using the global list of queuing time, without the global keywords. If you were to type and set and append list of queuing times nurse without setting it up in that function, it should still work, and it should pick up that it's outside the function, but it is extremely bad practice to do that, not least because if you were then to set up something else within that function, it would completely change the functionality of your of how that's working. So it's very good practice and the safest option to always say global when you're referring to something that does not live inside this function. Okay, so I'm saying here, I'm declaring a global variable. So I'm saying I'm going to be referring now in this function to list of queuing times nurse. That doesn't live in here, that lives outside. So when I say this, I want you to look outside this function. That's basically what it's doing. So I do everything as I did before. I calculate the time they started queuing, request the nurse. I then calculate the time they finished queuing, and then the total time they were queuing. And now at this point, whereas before I was just printing that message to say how long they spent queuing, now I'm going to append it to this list. And remember, this is a global list, so it lives outside of this generator function. So I can just call it by its name because I've already told Python that I'm referring to a global variable here, so it knows it's this one down here. And I'm going to append the time that I've calculated up here. Now, the beauty of that is that it means that for each of these, say you've got 100 patients going through your system, you've got 100 of instances of this activity generator that are being generated. Each one of those will be living and quite separately and doing its own thing. But when it comes to calculating the queuing time, it will then append it to this one global list that lives outside. So this will capture everything from all of those 100 instances, for example. And then everything else will work exactly as it did before. The only difference here is that I've set up my list to store my queuing times, that one that I referred to under global up above. And I put in an extra little thing on this one so that after it's run the simulation, so once it gets past this point, it's finished running the simulation. So I will then calculate the mean queuing time for the nurse because I've been appending them to the list for each patient. So because I've imported that nice little mean function from the stats package, then I can just call mean, give it the list I want to take a mean of, and then store it in mean queue time nurse, and then I'll print that out. So if I push F5 and run that now, runs, and you can see rather than a load of printed messages, it's now calculated the average queuing time for the nurse in minutes was 17.77 minutes. Okay, so and if I look in the variable explorer and look at list of queuing times nurse and open that up, all of these queuing times were from these 15 patients that came through. The first one had a queuing time of 0 because nobody was there in front of them. But all the rest had, most of the rest had queuing times of some sort. And this is the global list that we're adding to from each of those separate instances. So each of those activity generators, each one representing a separate patient, or separate patient's journey, I should say, was adding to this global list. And then all we had to do at the end, once it finished, was just take an average of that list. And that gave us the average. Obviously, if I were to run it again, might get something very different. So 37 minutes, 28 minutes, 9 minutes. So there's quite a bit of fluctuation there. And that goes back to the point that we made earlier about earlier in the course, that we don't just run these things a single time. We tend to run them lots and lots of times and then take average results over a batch of runs. And we'll come on to that a bit later. But for now, I just wanted to show you the kind of general structure. Okay, any questions about any of that?
Hi, Dan.
Hello, yeah.
Yeah, can I just check my understanding? Where we're requesting something, so say you've got there the nurse, you've got the nurse request. Am I right in thinking that you don't then explicitly have to tell SimPy and Python, right, the nurse is finished now? Is it just that once you get to the end of that with block, SimPy knows, right, okay, now you've finished with that that resource that's available for somebody else.
Yes, exactly that. So that's the beauty of using SimPy. So basically, SimPy is doing all the management of this stuff for you. So you basically just say, I need a nurse type resource here, and it will manage that, and it will freeze it in place until using the generation function architecture, but it will freeze that in place. SimPy is managing the resources that are being used underneath. So it will then automatically give that resource when it's available and do all that for you. And similarly, the other side, when that resource has finished with that patient, it will release it and then it'll manage what happens to it next. So yeah, that's the beauty of using something like SimPy. It's doing all that management for you, so you don't have to worry about that. I think I saw another raised hand as well.
Oh yes, this might be a question which I think you might cover later in terms of the number of simulations. But if you wanted to compare, a one flow pathway to another patient flow pathway, so for example, your first example to second example, and are there some kind of rules of thumb in terms of how you do this? Would that require like some cross-validation or a minimum number of simulations to compare like for like? Does that make sense?
Yeah, no, that does make sense. So the answer, okay, the short answer is no. What you tend to do, though, you tend to want to be able to minimize the variability that you're seeing. So you tend to want to get to a point at which your system is kind of stable and generating stable results. So you're doing enough runs where you're not getting huge amounts of diversity in the results that are coming out. And obviously, the more runs you do, the more the results will homogenize. And so you want to get to that point. And so one easy way to do that is just your stupidly high number of runs, and then you'll always hit that. But obviously, that might be practical for simple models, but for more complex models, that's not really too practical. So what you can do is you can kind of monitor the results with different simulation runs. That will give you an idea of the kind of, or monitor the spread of your results, I should say, and that will give you an idea about the kind of number of runs you need in order to get the right kind of results. There's also something that we'll come on to later called warm up, which is where well, we'll come on to it later, but it's basically within a run, allowing for the fact that real world systems do not typically start empty, and so you allow a warm up period, but we'll come on to that a little bit later. Any other questions?
Hi Dan, I've got a question about the random seed. I'm wondering if we can set the random seed, and if so, where do we set it?
Good question. Do you mean the random seed for the distribution sampling?
Yeah.
Sorry, I presume you said yes. Sorry, I didn't hear.
Yeah, I said yes, correct.
Yeah. Yeah, that's a good question. You can do it, yes, but I don't know offhand. I'll look that up for you. But yes, you will be able to do it. You can always set the random. Pretty much, I should be able to do it in everything that uses a stochastic drawing in Python. You can set a random seed. Obviously, for testing, that's useful, but you must remember to turn that off if you were doing it in reality before you generate your results. Otherwise, you'll get the same results. But it is useful for testing, so that you can replicate the same results again and again.
Okay, sure.
Okay, yeah, no problems. So let's set you off. I've been talking at you for long enough, and hopefully that started to sink in a little bit more, because I realized, just before lunch, I was just rattling through and said, here's SimPy. Look how easy it is. You just do this. So hopefully by going through this again and again now, you've started to see a bit of a pattern that actually it seems to be the same sort of things you're doing again and again. And once you've got that basic structure down pat, then actually it becomes much easier. But as ever with these things, always best to have a go yourselves. So I'm going to give you a challenge. Now, you can choose to do this individually if you prefer. I'd probably recommend in most cases you work on it as a group, because this is new to you all. So have a go at building this as a group. Make sure you're all following along as well. And what I want you to do is build your very first discrete event simulation model in SimPy of this system being described here. So we've got people arriving at a GP surgery every 3 minutes on average. They then queue to wait to be seen by a receptionist to be registered, which takes on average 2 minutes. and then they queue to see a GP, which takes on average 8 minutes. And then 3/4 of them sort of just leave the system there, but 1/4 of them come back in and go to see the receptionist again to book a test, which takes on average 4 minutes. And you've got 1 receptionist and you've got 2 GPs. So I want you to build that model, and I want you to run the model for 8 hours of simulated time. I want you to also add functionality to the model that will calculate and print the mean queuing times for each of the 3 queues, along with the mean total time in system. So that's the point at which they first arrive into the surgery to the point at which they depart. And bear in mind, there's apologies, that should also say sync down here. They do leave after. They don't forever stare at the receptionist in wonder after they've booked a test. So there should also be a sync down here as well. Hopefully you probably worked that out, so apologies. I'm pretty sure I said that last year and I said I'd correct it, but never know, one of these years I might. And for extra points, if you want to get extra Dan points today, it'd be great if you started plotting some charts, maybe a bar chart showing the times or some other stuff using matplotlib. So if you get extra time, because some of you might get through this a bit quicker, then have a go, put in some fancy bells and whistles, start trying out different scenarios in your model. So I'm going to give you about an hour and take a 5-minute comfort break somewhere within that as well. As I say, you can work individually if you prefer, but I probably recommend working as a group in most instances for this, particularly as it's your first time using this. Yes, Andrea, you got your hand raised.
So I wasn't quick enough to copy all of the code into Python that you've just gone through. Can we see it?
Oh yes, yeah. So you've got access. So all of the let me show you on GitHub. So on the GitHub repository for this session, which is 3B, isn't it? That's not, it's module 3. There we go. So in here, in session 3B, you'll have a folder called lecture examples. All of the examples that I show you during the lecture are all stored in here. So the 4 that I've just shown you are SimPy 1 to 4. So 1 was the basic model. Then 2 added the second process in a linear way. 3rd one was where you did branching paths. And then the 4th one is where you started storing results using the global keyword. So don't worry about 5 to 8 for a minute. That's what we'll come on to in the second half this afternoon. But 1 to 4 are the ones. And that goes through all of the lectures. I'll always put the lecture examples up so you can view those pieces of code yourself. Okay. Let's stop sharing. I'll open up the groups and have fun. And the key thing here to say is that you should feel very proud of yourselves today, because in the next hour, you're going to build your very first model. And that's, I think, quite an accomplishment, given many of you had never coded before. Most of you, certainly not in Python, just 1 month ago. So to now think that you're now building an advanced operational research discrete event simulation model, something that you could actually now take away after today and build this stuff for your own organization, your own queues and systems. Just take a moment to reflect on that, because that's quite a jump that you've made in a month. So go into this with a smile beaming on your face, thinking how far you've come. Okay, so I'll stop sharing there, and I'll shut up about beaming smiles, and off you go and have a bit of fun. Okay, welcome back, everyone. So hopefully you've had a bit of a chance to play around with that. I know a few of you, quite a lot of you, were doing that sort of individually, but I did see a couple of the teams having a go at that as a group as well. It was lovely to see so many of you getting excited when your code works. It's a really nice feeling. I think you'll agree when you get a model working, and obviously this is the first model that you've built, so this is fantastic, and it's a great feeling, and it's fantastic to know that you can sort of go away now and you can build these models. You've actually got enough information to be able to do these, and hopefully you've got a bit of a sense about how they work. Now, I am going to share the solution with you, as I do with all these, but I did think it might be more useful just to get some of you to talk through your solutions, because you've heard me explain the same thing over and over again. So I'm first of all just going to ask if there are any volunteers who would like to talk through. Otherwise, before I sort of pick on someone. So if there are any volunteers who would like to talk through their code, please do raise your hand. Okay, that's as I expected. In which case, what I'm going to do, there were a couple of groups I noticed were working on this in their groups. So I'm going to pick on one of those groups. So I'm going to slightly fudge the wheel here. Let me just bring back up the full wheel. Open that. And I'm going to pick on two groups in particular, which is Talkie Toaster and HAL 9000, who are both working on this as a group. So I'm going to spin the wheel. You've now got a 50-50 chance that it's going to be one of you. So hopefully you've got somebody ready who can talk through what you've done. So I'm going to click and spin the wheel. Oh, yeah, no, I think it's going to be HAL. Yeah, it's somebody from HAL 9000, please.
Could I ask you a favour,
It's Talkie Toaster's got the raw end of the deal for the future one. So yeah, somebody from HAL, please.
I'll say, Irma, would you mind talking through it if I share my screen?
Yeah, I can do.
Thank you.
Okay, let me just bring up also the slides.
I'm not sure if it's just me, but I can't seem to hear anything. I'm not sure if you're talking.
Can you hear me?
Can you hear me?
Yeah, I can hear you.
I can hear you all fine.
It might be you, Dan.
Okay, I can see in the chat that that people can hear you, so please do carry on. Apologies, I'm not sure why Zoom suddenly decides not to cut off my sound, so please carry on, and if you can just stop sharing when you've stopped. Oh no, you've stopped.
Okay, so we have the function generate arrival to GP, which obviously generates patients as they arrive to the GP practice, and then so we have the mean arrival time, the entities, receptionist, GP, the resource, mean registration, mean consultation, mean time to book test. And we're passing through the patient ID as well. And then we are generating the activity by passing through the resource, receptionist, and GP, and then the mean registration, mean consultation, and mean time to book the test, and the individual patient IDs. And we are doing this in the while loop because we are taking the mean arrival time random and then generate increasing the patient. And then in the generate patient function, so we have patients entering the registration. That's the timestamp there. I think we just started adding the list of queues. We haven't actually finished with the global list of queues there. So I'm going to ignore that for now. And then we request the receptionist resource and hold on to it. And then we take the time when the patient leaves the registration and calculate the difference between the time they entered and left the registration, print that, and then we take a sampled registration from the mean registration, using the mean registration. And then the next queue is the GP consultation. So we request the GP resource. First of all, we timestamp the queue for the GP. So that's line 48. We then request a GP resource. So similar thing, really. Well, almost the same thing. Time between GP consultation minus, and the ending of GP consultation minus the time of arrival to GP consultation, and then the mean consultation. And then at the end, we decide if they need to do a test or if they are out. So it's a random from a uniform between 0 and 1. And if it's below or equal 25%, then they will need a test. So again, we have, they enter, we timestamp when they wait for the receptionist, and then we request a receptionist resource, and then it's the difference between the time it takes for the receptionist minus when they started to wait for the receptionist, and then it's the sample time spent from based on the mean of the receptionist. It takes 4 minutes. And then finally, we call this whole thing. So our mean arrival is 3 minutes. Our mean registration is 2 minutes, 8 minutes GP consultation, and 4 minutes booking the test. And we call the whole process, and we run it for, was it 8 hours? Which was 480 minutes.
Oh, it did work.
Because we did, because we just started adding to the list, also saving to the global list. If you comment that out, it will work.
Fantastic. No, thank you very much. Sorry, I managed to get the sound back shortly after you started speaking, so I caught most of that. Really nice description as well of how that works. And I wanted to get one of you guys to talk that through, because it's a really good way to make sure that you understand it as well. And considering you only learned this a couple of hours ago, this is a really nice description of what's happening. So really well done, excellent work, really good. And I see sort of pouring in on Slack. There's lots of examples of the code that people have done, which is brilliant. So really good work. Genuinely really impressed with this. It's a big thing. Don't sell yourself short on what you've just managed to do so far today, because you have just built a model, an operational research model, and as I say, a month ago you most of you didn't know how to code in Python. So I think that's a big achievement. Okay, so what I'm going to do now, I will carry on. There's a little bit extra I want to talk to you about, and then you can have a go at another exercise. A number of the questions that came up in one of the groups, a lot of the stuff that you've probably already seen starts to get a bit messy with this stuff. That's solved by the object-oriented approach. So when we come on to that in the advanced session in part 2 in a few weeks' time, you'll see how you can make this a lot more elegant, particularly for bigger models where that becomes more important. Okay, right, hopefully this will work well. So let's switch back. No, we're not there. Where are we? Here we are. Right, okay, so let's talk about, first of all, about multiple generators. So when we were talking this morning about generators, we said that, it's quite possible in a lot of systems that you will have more than one way for your entities to enter our particular system. They might enter in different ways, but go through the same set of processes. Or they might go through completely different processes, or they might go through some of the same processes and branch off in a different way. And we can deal with that in different ways. So it might be that people arriving at the ED, the same things happen to them, but we might want to model the ways in which they present to ED slightly differently because they may arrive at different rates. So we want to capture that, and we've got separate data that tells us what those arrival rates look like. Or it might be that depending on the way in which somebody arrives into a system, what happens to them after might differ either completely or slightly. So, you know, at an ED, you know, whether they're self-present or by ambulance, it might be that exactly the same things happen to them. Or in our GP surgery example, we saw that people were coming in to speak to a GP, but there are also people coming into the same system that had nothing to do with that, and they were just coming in to see the nurse for a test or for the weight loss clinic. So different processes happening, and we can deal with that in the same sort of way. And it's actually really easy to have multiple entry points to our model in SimPy. All we do is we just set up more than one entity generator. So let's look at an example where we're going to model this system here, where we've got, this is from earlier, the simplified version of what we looked at this morning. So we've got people coming in for a weight loss consultation with the nurse, and separately we've also got people coming in arriving for tests with the same nurse but a different process and a different arrival rate. Okay, so we've got two different, in this case we've got two different generators and two different things that are happening to them, albeit with the same resource. Okay, so that resource is going to be shared across these processes. So let's bring up SimPy 5 so you can see how this works. So this is all the same as before. This particular arrivals generator, this one here, is going to describe people coming in for the weight loss clinic. So exactly the same as we coded it before. But then this time we've also got a separate patient generator. Here we've got another arrivals generator function, and this one is going to have a different inter-arrival time, so we can express a different rate for people coming in for tests as for coming in for the weight loss clinic, and also different activity times, because in this case they're coming in, they're using the same nurse, but they're coming in for different reasons, so the test is likely to have a different activity time compared to coming in for a consultation on weight loss. So in the patient generator function, we start running, create an instance and start running the activity generator for weight loss down below, as we wrote it before. But in the patient generator for tests, we actually start a separate activity generator for that one. So I've written a separate activity generator that describes what happens when they come in for tests. So essentially what we've got here now is two separate patient generators and two separate patient journey generators. We can call those depending on how they're coming in. Now, obviously, if they were coming in different ways at different rates, but the same things were happening, then we could just use the same activity generator. And we wouldn't need to have, we just need separate patient generators. But in this case, different things are happening to them, even though they're using the same resource. And a question came up in one of the groups about how it knows how to distribute the nurse resource, how it's going to do that. This is the beauty of using SimPy. SimPy is doing all the magic for you in the background. Basically, underneath all this, SimPy is managing everything. So it knows how many resources it's got and what type, because you've told it what you want. And basically what SimPy is going to do underneath is say, okay, well, the nurse resource is needed over here, but it's also needed over here. And this patient arrived at this point, and assuming you haven't got a priority system, that patient arrived first. So I'm going to give that the nurse over to that patient. Now, you can imagine without SimPy, that would be quite messy. You'd have to code all that manually, and all that logic about what happens, where you need to give the nurse, etc. SimPy does all this for you, and that's the beauty of how simple it is to code using this SimPy framework. And everything else just runs exactly the same. The only difference is that here we've now got two arrivals generators that we need to start up before we run the simulation. So we've got the weight loss one, and we've also got the one for the tests as well. And obviously we're passing different things in. So for the weight loss one, we give the weight loss inter-arrival time and the mean consultation time for a weight loss clinic, but we pass in the nurse. And for the test one, we pass in the test inter-arrival time along with the mean time for a test, and also the nurse. It's the same nurse resource, it's just we're using them in different places. Okay, so it really is as simple as that. If you want more than one way in which patients come into the system, you just write another generator that will deal with that. And if you need them to go through different processes, you just write a new generator function that describes those processes. So it's as simple as that. And to think about your activity generators essentially is describing a journey. So this is a journey, and the journey won't be the same for everyone because you might have branching paths, but you're essentially thinking about one journey. So this is the weight loss journey for patients coming in for a weight loss consultation versus patients coming in for a test. And you could, in theory, have exactly the same generator function and have an attribute of the patient that's passed in that says which branch they go down. But it's good to separate those things out. It's much simpler to do that when we come to look at the object-oriented structure, which is another reason why it's a better way to do it. This is the raw way, but this is the way that SimPy will teach you how to do it. So the SimPy tutorials will teach you how to do it raw first without using object orientation, because it gets you used to using the generator functions, which are the heart of how this works. Okay, so that's fairly straightforward, how we can add in multiple ways into the system. Now, we mentioned earlier, and we've mentioned before in this course, that when we have a stochastic model, which I would imagine all of your models are going to be stochastic, at least in some way, it's really important that we don't just run the model once if we're looking to draw insights, because, as we talked about before, each time it's running, it's randomly sampling. And that means we could end up with a run of good luck or a run of bad luck, which isn't representative of what's really happening, or happening normally. So you could, for example, have a run of your simulation where it sampled unusually long activity times. You had a load of patients that were spending hours with the nurse. That could happen by random chance. It's unlikely, but it could. Or you could have really long inter-arrival times, which would be a run of good luck if you're trying to minimize waits in your system, i.e. patients aren't arriving too frequently. So what we need to do before we go using this model to inform any decisions and pull out the results that will do that, we need to run a stochastic model many times and take summary statistics over those results so that we get more representative results from the model. So we're not just taking it from a single run, we're running this lots of times and seeing what tends to happen on average. So to do this in SimPy, the way we do it is we put all of the setup, that's all of the stuff where you set up the simulation environment and your resources and your parameters, all that sort of blurb that came after your generator functions. We put all of that, including the establishment of the environment itself, in a for loop. And basically the for loop, the range of that for loop is the number of runs we want to run. So if we say, for I in range 100, if you want to do 100 runs, and it'll do all that 100 times. Now, what that does mean is that because you're doing all that setup each time, and you're setting up a new simulation environment, the simulation will reset and start from fresh after every run. So if we want to capture any of the results from a run, which we're going to need to do if we want to calculate averages over a batch, we're going to need to do one of two things. We either need to have some sort of global list outside of that for loop that will store the results from each run, so that after the run, it dumps the results from that run into that list, and that operates outside of that loop. Or we could just write the results of each run to file. So we do exactly as we did before. We calculate that, we get all of the patient waiting times as they're happening. Then at the end of that run, we take the average as we did before, and then we write that result to the file so that we know for the first run, this was the average value that we got. So let's have a look at an example of that in SimPy 6, where we're going to take exactly the same model that we've just looked at here, but we're going to, so with the separate weight loss and test generators, but we're going to add in multiple runs. So all of this is exactly as it was before, no change whatsoever. The only difference here is I've made a couple of extra imports. So I've imported CSV, which you'll remember using in one of the introductory Python sessions. Allows us to read and write CSV files really easily, so that'll come in handy for us. And I'm also going to import pandas as PD, because then I can store my results in a pandas data frame against the run number, and that'll make it nice and easy to look that up. So all of this is exactly identical as it was before, so I'm not going to go through that. But here, where we start to diverge from what we did before. So we've got our generator functions, they're all written. Then after this, I've just added a bit in here where I set up the number of simulation runs. Now I could just specify and hard code that in the for loop below, but it's good practice to separate that out, so I can easily, if somebody wants to change that, they can easily change that number of runs on the separate line here. So I want to make it 1,000, I can just very easily change that. What I'm also going to do before I start this for loop is I'm going to create a file which stores the result of each run, and that's going to be the file that will store those results, CSV file. And before I go through the for loop, I'm just going to write a couple of column headers so that I've got headers on my columns, so that when I come to read that in after the simulation's finished running its batch, then I can see what the results relate to. So you'll be familiar with this from the file reading and writing stuff we did. That again, we're using that with statement. We're opening this file called nurseresults.csv in write mode with a W. Now remember, because it's being opened in write mode, if that file does not yet exist, which it won't the first time you do this, unless you've manually created that file, then it'll create that file. So if it doesn't exist yet, it will create that because it's in write mode. And then all I'm going to do is I'm going to set up a new CSV writer with a delimiter of comma. So to say it's a comma delimited file. And I'm just going to write a single row initially, which just has my column headers. So it's just going to be the list run and mean q nurse. So there'll be my 2 column headers. So this will basically create a new file or overwrite the file if it already exists. And it will write those 2 column headers there. Then I'm going to run my simulation for the specified number of times, which I've specified up here as 100. So we just put everything we had before, but in a for loop. So I just said for run in range and then number of simulation runs, which is 100. I do everything as I did before. I set up my SimPy environment, set up my resources, my parameter values. I'm going to set up my list to store my queuing times. Remember, that's the global list we refer to up here. And then I start my arrivals generators. Remember, we've got 2 of those. And then I'm going to run the simulation. So that's a single run of the simulation. We'll run for 120 time units, which is minutes here. So it's 2 hours. Then I'll do as I did before. I'll calculate and print the average queuing time for that run. So all of the patients, the queuing times as they come in, we're calculating them, storing them in this global list. Then I can take them at the end of this single run. I can take the average for that run of the average queuing times. I'll print out a little message as well. And then now I've got the results from one run, I will now write those results to file. So I'll add it to my file. So what I'll do, I'll just put them in a list because that'll make it easy to write. The list to write is going to be made up of the run number, which remember I'm storing up here, I'm using it as the iterator in my for loop. Obviously, if I don't change that, the first run will be run 0. You may choose to change that to run +1, in which case you'd need to change this as well to +1. And then, so I'm going to store the run number against whatever the mean queuing time I calculated up here was. So from the first run 0, it'll calculate the mean queuing time as we did before, and it'll write that out to file. So here I'm putting that in a list, and then here is where I store it to file. Now here I'm opening it in append mode, and you'll remember from the file reading and writing that if we open a file in append mode, that basically means we want to write to the file, but rather than starting at the start of the file, which would overwrite it, we start from the end of the file, which is what we want here, because each time we want to write a new row for each new run, and even on the first run through, we want to append because we've already written up here our 2 column headers. We don't overwrite those, so we always write in append mode here. And all I'm going to do, create a new writer as I did before, and then just write that list. So the first time before it goes through that loop, it'll write the column headers, and then it'll run one run of the simulation. It'll calculate the average queuing time, and then it'll store that against the run number and write that to a list. So it'll do that, in this case, 100 times. It'll go through, and each time it'll add a new entry to the CSV file. Then once all of that is finished, so once we've gone outside of this for loop, we've done 100 runs at that point. So now down here is everything after we've done our batch of runs. So what we might want to do, for example, is to read that back in and grab some summary statistics. So here I'm just going to use a pandas data frame to do that. So I'm going to read in using the pd.read CSV file. And I can't remember if I showed you this function yet or not, but it's a really handy function, which basically is a nice feature of pandas. I think I mentioned it, I don't know if I showed it to you, which allows you to read in any CSV file and it'll automatically store it in a pandas data frame for you. It's really handy. So you don't have to go through and do all of that stuff that you did before with, setting up a new data frame and then reading in lines one by one and then putting them in different lists. And then you don't need to do any of that. Just say pd.read CSV, give the name of the CSV file, and it'll do all that magic for you. And that's part of the reason I've given column headers here, because it will intelligently, if there are column headers in the CSV file, it will give the column names in the pandas data frame as whatever the column headers are, which is exactly what we want. So I'm going to read that in. That will be stored in a data frame called results df. That single line of code will do all that for me. And then, for example, I might want to take the average queuing time across the runs. So I remember in pandas, we can do that really easily. I just give the name of the column, the name of the data frame and the name of the column. So results df mean q nurse. Remember, the column names are whatever I set the column headers to here. And I just take the mean of that. And then I can print that out. Maybe I want to take the minimum and maximum. So I can, again, use the max and min functions in pandas as well and get that out really easily. And of course, there's lots of really, much cleverer stats that you can do in pandas data, in a pandas data frame other than mean, min, and max. But this will give us a nice sort of overview about what the average was, what the longest queuing time was, what the shortest was. So if I run that and push F5, now that's done it very quickly because I've got a very fast computer. You may find yours is a little bit more delayed, although it's a fairly simple model, so it should be okay. So here we see the 100 runs. These are the average queuing times for each of the individual runs. Before, we were just running it once, so one of these numbers would have popped out, depending on whatever our random run of luck was like. But this time we've run 100 runs. We've stored all the results to file as we've gone along, and then we've read that file back in, and now we calculate a mean. So now the mean queuing time over those 100 runs we see is about 23 minutes. The longest was about 60 minutes, and the shortest was about 3 minutes. Now, if I run that again, you should see, now we've got a much closer. So we had about 23 minutes, 23.6. So again, much closer. If I run that again, 22.5, again, about 23 minutes. So we're getting much more stability in our results now. And this is the kind of result that you should be reporting, not a result from a single run. The only time you should report a result from a single run is if everything is fixed in your model and it's not a stochastic model, which is going to be highly unlikely for anything that you're doing. But you can see, we can say now with confidence that it seems to be about 23 to 25 minutes on average people are spending in the system. They could spend up to an hour, and they might spend just a minute or two. And of course, I'd get even more stability and accuracy if I were to increase the number of runs. So if I increase that to 1,000 and to run that, and there we go, that's run through. And again, we see about 24 minutes there. Run that again, about 24 minutes. Run it again, 24 minutes. So it seems 24 minutes is probably about the number. Okay. And the question came up earlier about, how many runs to do. And again, you've got two tactics. You can just run it, if it's something simple like this, just run it lots of times until you're getting that stability. Or you could monitor how stable it is over time and where that stability tends to work. So you could try it with 10 runs versus 100 runs versus, etc., etc. But that's all you need to do. So you're just basically putting everything in a for loop and then writing to the file as you go along. Now, another really important concept that I, again, briefly mentioned earlier is that of a warm-up. So a particular problem with discrete event simulation models is that what they do is by default, we assume that our system is empty of entities when the system starts. So when you've just written your model this afternoon, looking at your GP surgery, there were no patients in the system when it started. Now, in some cases, that might be fine. For example, if we're simulating a day in the life of a minor injury unit, at the start of the day, there will be no patients in there. They'll turn up from when it opens. And if we're modeling it just till the end of the day when it closes, that's no problem at all. You don't need a warm-up because you would expect it to be empty. That mirrors what we see in reality. But imagine we're modeling something like an emergency department or something else in a hospital. Those systems are never empty. There's always patients in those systems. And so if we were to run our model starting from empty, then the problem is our results are going to be skewed by the fact that towards the start of the simulation, there weren't very many people in this in the model. So the waiting times are going to be very short at the start because there was nobody queuing. So you're going to have people at the start of your simulation in your ED who are seen and treated very, very quickly. And that's likely not to be representative of reality. So what we want is a solution that allows us to somehow capture the fact that our model is our system that we're modeling is not going to start off as empty, assuming that's how your system works. So to do this, we can use something called a warm-up period. Now, basically, what a warm-up period does is it runs the model as normal, but during the warm-up period, it doesn't collect any results. So it just lets it run, but it doesn't collect any results. It doesn't include that in any of the results that are being generated. And what that allows the simulation to do is to get to a kind of steady state, a more representative state, before we start collecting results. Now, the length of the warm-up period that you need depends on whatever it is, whatever system that you are trying to model. Now, one tactic is you could just set a really, really long warm-up period so that you know by that point it will be fine. It'll be sufficiently chaotic that you can start collecting results. Or we might try and do something a bit more clever. And we might run the simulation multiple times and then track the results over time to see when a kind of steadier state appears to have been reached, when we're reaching that kind of more stable equilibrium state. Doesn't matter however you do it, but either way, it's really easy to add a warm-up period to our SimPy models. And we do that just using some simple conditional logic, which basically says, don't collect these results, don't collect any results, don't include them in our recorded results until the warm-up period has passed. So let's just look at an example. So if we go to SimPy 7 here. So again, exactly the same model as before with our weight loss and test journeys and two different generators. So exactly as we did before. The only difference here is that if I scroll down to the bottom first, if I can find it. Where is it? Oh, here it is. Sorry, I couldn't see it for looking. Right, so you'll see down here, so if I'll come back to the generator functions. So where I set up the number of simulation runs to do, which was 100, I'm also going to set up two extra parameters here, one of which will be the results collection period, and one of which will be the warm-up period. So the results collection period is the period after the warm-up period that you want the model to run for and start collecting results. The warm-up period is the amount of time you want the model to run for before this, where you're not collecting results. Okay, so the total amount of simulation time that's run will be the warm-up period plus the results collection period. So in this case, we're going to run it for 240 minutes, 4 hours. But the first 2 hours worth, we won't collect any results, and we'll only do that in the second half, the second 2 hours. Okay, so in order to do this, all we need to do is wherever we're going to go and add some results. So here, where we're calculating the queuing time, and then we would normally then append that to that global list. Before we do that now, we just make a simple check using an if statement. We check the current simulation time, which remember you can grab out using env.now, and see if that's greater than the warm-up period. Have we passed the warm-up period? If not, then this will never get appended. And in fact, it doesn't matter for this, but in reality, you'd probably want to put all of the calculations. So you're not wasting time calculating in a more complex model all of this stuff when you're not going to append it anyway. But just for simplicity here, I've just put it on the append statement. Yeah, so we're basically going to append if we've passed the warm-up period, then this line will kick in as it did before. So the model will run and patients will be coming in and they'll be queuing and causing issues and doing all sorts of things that patients do, but none of their results will be collected until the warm-up period has passed, and then we'll start looking at these results, looking at the queuing times. Okay, so that's all we need to do. We just set up a warm-up period and we specify it here. We specify it here, and then we check to see whether the warm-up period, the current time in the environment has passed that warm-up period. And you'll see up here, because warm-up period is a global keyword, global variable, I've specified it as a global variable here. So I'm saying when I refer to warm-up period, it's not something in here, it's something outside of this function. And then down here, so this is where I specified the warm-up period and the results collection period. So the only difference I need to make down here is where I go to run the simulation. Before, I would hard code this and say however long I wanted to run the simulation for. But now I'm telling it to run for the sum of the results collection period and the warm-up period. And it's good practice to do that, and specify those things separately, and then just say it's the sum of those two things. So that you can very clearly see, and anybody using this model can see how long it's going to run as a warm-up where it's not collecting results, and then after that, how long it's going to run where it is collecting results, so that it's very clear now that it's going to run for a total of 240 minutes. And that's all there is to it. That it's as simple as that, but it's very good practice. And unless you are modeling a system that you would expect to start empty, then which you may well be, depending on what you're modeling, that you should start with a warm-up period in your model first. Yes, Andrew, got a raised hand.
Yeah, I'm not sure if it's a quick one, and apologies if you're going to cover this later on, but it's been nagging me for a while and we've not seen it answered yet. Is it generally good practice, if you're doing something like this, to just look very quickly at what your overall capacity of your system is? So it's clear in the example you've given us here that there aren't enough nurses, and it was clear in an earlier one that there aren't enough GPs. So if you run your model for longer, your queues just go up and up and up. So is it generally worthwhile actually saying, before we do the simulation, just take a few averages and see? And I guess kind of linked to that, am I correct that when you do these runs, it's doing it on the averages for people who have completed the pathway, but in fact there'll be a load of people still left over in the queue that you're not including in your averages here?
Yes, so if I go on to the second point first, yes, you're right. So the way we're doing it at the moment is only capturing people who've completed a queue, because now you don't have to, obviously, because this is Python, you can put in whatever logic you want. So you could have it so that you are flagging up people who started in a queue, but then they didn't finish in that in the time of the model, and you would need to decide what you need to do about that in terms of what assumptions you're going to make, or how you want to highlight that. You would so obviously it depends how you want to do it. In reality, you'd probably have so many patients for the sort of systems you'll likely be modeling. You'll probably have so many entities going through your system over such a long period that the odd one that's still in the system at the cutoff point isn't going to make any difference to your overall results. Obviously, in something like this, where it's smaller scale, it would make more of a difference. So that's absolutely right. In terms of the first question, you're right. I mean, so there are. So in the examples we've looked at, it's clear, as you say, that you've got insufficient resource capacity for this system. That can be an important thing to demonstrate using a model, even if it looks blindingly obvious that there's clearly a problem. But just showing people the scale of the problem and what that actually means, and sometimes having so in reality, obviously, you could end up with building a model that says, okay, I've run this for 2 days of simulated time, and now patients are waiting 5 weeks to see in the waiting room to see a GP. Now, obviously, that will not happen in reality, But what that could be exposing is what's known as a hidden queue, where actually you're not getting through enough resource. You're not getting through enough of the activity, sorry, that's coming in. And what's actually happening is you're then sending them away again, and you've got a hidden queue building, which is likely going to burst over somewhere else, probably if it's a GP surgery into ED, for example. So actually just showing that and just showing, look, to actually meet the level of activity that we've got coming in, if assuming we had infinite capacity, this is what saying would, the model saying would happen, can be a really important result to talk about, and to see, to show people how the extent of the disaster in the system, essentially, which can sometimes be hidden in the real world system. So yeah, that can be an interesting thing in itself. And don't ever think as well that something's too obvious to be shown by a model. You'd be amazed how powerful having a model that plugs in their own data and that shows them something that you think you can see is going to be a disaster, but just showing people this and showing it work through and in a virtual environment where it's safe, and showing them the disaster that this means, can be really powerful. So yeah, that's a really good point. But part of your sort of decisions you make as you're designing the model will help guide you on how you approach that. I think there was another hand up as well.
Oh yes, I'm just trying to get my head around the sort of theoretical side of the warm-up period. Is it always necessary to have one? And I guess the sort of opposite question is that if you didn't have one and you were trying to compare models or trying to look at a model, is that your model invalid if you don't have it?
So you don't always have to have one. As I say, if your real-world system starts from empty for the period you are modeling, like you're modeling and like say an MIU where people are turning up and it opens and closes, and therefore in the morning there's nobody there, so it's empty, then that you don't need a warm-up period, because in fact by putting one in that would be invalid. But where you've got a system which is not starting from empty, it would be invalid to create a model that does start from empty, unless you were modeling it for a very long period of time. So if you were modeling your ED, you started it from empty, but you're collecting your results over a simulated 5-year period. I don't recommend doing this, by the way. But if you were doing something like that, it wouldn't matter, because the initial results which are a bit skewed will be so diluted by everything else that it would be irrelevant. But yes, if you're modeling over a more realistic, sensible time period, and your model does not start from empty, sorry, your real world system does not start empty, then you should absolutely be using a warm-up period, because it will affect the results if you don't, because it'll typically make the results appear much better than actually in reality they are. Ian, I think you had your hand up as well.
Hi, sorry if I missed something, but I just wanted to ask about the exporting to a CSV bit. And because were you doing that just to show us that you can? Because wouldn't it be easier just to put the data directly into a data frame?
Yeah, so in this situation, yeah, so in part that is showing you that you can. I would typically, for very large scale models, so for something like this that runs in half a second, it doesn't matter. But you could end up with models that take, if you had a very big model that takes days to run. And if you've got something like that, it's very good practice to be writing out to file, because if anything happens to your simulation halfway through, or somebody accidentally crashes or turns off the computer, particularly if you're using sort of cloud computing or something like that, what you don't want to happen is everything to be lost. And obviously if you're only storing it internally in the program, in the memory, that'll all be wiped. So it's quite good practice to write it out to file, so that then if anything did happen, you can see where you got to. You say you may have got through I don't know, 500 of your 1,000 runs, and so then you could just start it running from and just run another 500, rather than having to start completely from scratch. So it's good practice to get into, even for smaller stuff, where it's not so much necessary, but it's also useful. It's easy to be able to share your results then, so you could then be able to share the output with somebody else. It's just a CSV file, and they can easily see the results and interrogate the results that were generated. So generally, yeah, it is good practice to export to file in some way.
Thank you. Thank you.
Okay. Oh, I've got some more raised hands. So if I can just take one more question before I move on.
Sorry, just on top of that, is it going to crash the CSV if it's, you know, getting days of simulation, or is it generally okay?
No, you should be fine. I mean, so what you don't want to do is be in a situation where you're exporting out to Excel files, because yes, you will very quickly run into that. You can have incredibly large CSV files with no issue. I'd be amazed if any of you are writing models that generated CSV files so large it crashed your computer. That would be highly unlikely. And if they are, then I would question that you might be storing too much information in terms of what you're storing in the file. So remember, you're just trying to store summary information from your runs, for example. You're unlikely to want to store every last piece of information about a single run, because remember, it's just some random numbers. That's all it is. So that's unlikely to be useful, just to run a single, capture every piece of information from a single run. Okay, I know there's maybe some more questions, so if anybody does have any questions, obviously just do post them in the chat and Slack. But just in the interest of time, I just want to carry on. So that's warm-up periods basically, and you can see that you can add them in really easily. The last thing I just want to mention is something called containers. Now, containers are so far when we thought about resources, we thought about resources as being these discrete identifiable entities. So we've got 3 nurses, we've got 4 beds, we've got 5 GPs, whatever it may be. Okay, but what about if our resource was continuous, or if we wanted to somehow model a kind of a homogeneous mass of resource? So imagine that we were modeling the fueling of a car at a petrol station, and our resource then was petrol. Well, we wouldn't say the way we want to do that is to say how much petrol we've got in terms of being a continuous quantity. Or for something that might be more related to stuff that you'll be doing, imagine that rather than modeling a number of nurses, that actually you wanted to model simultaneous nurse time in use, from which we kind of take from and add back to a pool of time as the various activity fluctuates. And in fact, I've done that when I've done some modeling at the very start of the pandemic. We were looking at end-of-life care, and in particularly for sort of things like community nursing, where they're trying to plan on nursing hours and how many nursing hours do I have available for a certain day. So it might be that actually using a container might be more appropriate to express your resource rather than the individual nurses, depending on what your model is, what it's modeling, and what questions obviously you're trying to answer. And so we can use, rather than a resource class in SimPy, we can use a container class for those kinds of problems. So let's have a little look at an example in SimPy 8. So here I've basically got an arrivals generator here and an activity generator here. My arrivals generator is basically going to generate some new arrivals that are coming into the system, where they're going to be visited by some district nurses. And then in my activity generator here, I'm going to, much in the same way as I did before, that I will basically want to create this activity, emulate this activity, but I'm going to do it slightly differently here. So if I scroll down first of all down to the bottom where I set up my resources, here normally we'd say simpy.resource, we give the simulation environment and we give the capacity as being the number of resources we have. Here, rather than a resource class, I'm using the container class of SimPy. So I say that district nurse is a SimPy container. I pass it the environment, and then I pass it the number of units of stuff in this container and the total capacity of the container. So init specifies the initial level of the container, and capacity is the total level that this can take. So you can't go beyond that capacity. Now, here, it's going to make sense to keep those things the same, because if we end up putting back more district nurse hours than we took out, then something's gone wrong. But in some situations, you might have a container that goes above the initial level that we specify. So you might have an initial level of 1,000 units of stuff, but actually, you've got a total capacity of 10,000. You might gain resource in some ways. Think about the petrol filling thing. You might start with 1,000 liters or whatever it may be, and then the tanker comes along and fills up, and you've suddenly got more in your fuel pump. So the way we do it is similar but a little bit different. So all of this is the same as we saw before, just setting up the queuing times and everything like that. Excuse me. We set up the time they started entering the queues before. Then here, what we're going to do is we're going to calculate, rather than the amount of time. So rather than before, we said, grab me this resource and then freeze this function in place for this amount of time that I sample. Here, we're doing it slightly differently. Here, what we're going to say is I want you to randomly sample the number of minutes I'm going to take from my pool of district nurse minutes. Okay. So I'm going to randomly sample that in exactly the same way as I did before. It's just that's going to represent something different now. And I can use the level attribute of a container to find out what the current level of the container is, i.e. how much we've got. So at the start, there should be 1,000 when we first run that model. Then I'm going to take some quantity of this unit from the container. So if I sample that I want to take 20 minutes of district nurse time, then what I can do down here is I use the yield keyword, and I use the get method of the container. So remember, district nurse is a container here, not a resource. And I use the get method, and into that I pass the number of units of stuff that I want to take out. So in this case, it's however many minutes I've sampled. So if I've sampled that I want to take 20 minutes of nurse time for this particular activity, then that's the amount I will take out. So my level will then go down from 1,000 minutes available to 9,980. So then I can print out the message what the level is now. At this point, after this yield statement, this is now when the patient has left the queue. So this will basically freeze the function in place until that number of units of stuff can be given. So in the same way before we used the with statement, here we're saying I need this amount of resource, and it will freeze in place until it has that amount of resource available. Now, be careful, because if you omit the yield keyword, the program will still appear as though it's working. In fact, it will work, but no queues will ever form, because what will happen is it will always just take the amount it requires, even if there aren't enough units of stuff available. So do make sure you use the yield keyword there. So if we get to this point, then we know that they've essentially left the queue, because that amount of stuff, in this case district nurse minutes, is available. So we can calculate the time they left the queue and do as we did before. And then, just as we did before, we're going to call a timeout, where we're going to essentially freeze in place for the amount of time sampled. Now, in this case, the amount of stuff that the stuff that I'm taking out, the resource stuff, is a unit of time. That may not always be the case. It just so happens in this case that I'm taking out the amount of resource I'm taking out is a district nurse unit of time, and therefore I'm going to hold that unit of time for that amount of time. But that may not be the case. Imagine you were filling up with petrol. You may take out a certain amount of petrol, but the amount of time that takes will not be, or it's unlikely to be, the same as the amount of petrol you're taking out. So just be aware of that. It just so happens here, because the unit that I'm using in the container is time, that I'm freezing for that same amount of time. Now this will do in the same. So before, when we had a resource, we were basically using the with statement and saying keep hold of this resource for this amount of time. Here what we're doing is we've basically drained whatever we've sampled, say 20 minutes, out of our pot, and that 20 minutes will remain drained until we can go back and put it back in again. So essentially we're timing out, we're freezing. We've now got this drained pot. Once that time has elapsed, in this case, I'm going to put some stuff back in. Again, that's not necessarily going to be the case. If you're modeling a fuel pump, you don't, after you've put all your fuel back in, fuel into your car, you don't then siphon it all back into the gas tank, into the petrol pump, unless you're slightly mad. I think that would be quite an odd thing to do, unless you just really like siphoning petrol for fun. So just be aware that you won't always do this, and that you may have a separate method that represents the tanker coming along at certain intervals and putting some units of resource back. But again, because I'm dealing with district nurse time here, I'm taking out an amount of resource. I'm taking 20 minutes of district nurse time. That's come out of the resource pool, and then once that time is up, I can then put those district nurse minutes back in. So I use the get method of a container to take units out, and I use the put method of a container to put units back in. Everything else is exactly the same. That's the only difference, other than the way you set up the capacity there. So probably most of you won't use that, but it's worth just flagging up that there is a way of doing it if you do want to capture a resource that is more of a sort of homogeneous mass of stuff, rather than an individual stuff or staff resource, if you like. Okay. So unless you're feeling very ambitious, I probably wouldn't recommend trying to do this in 11 minutes, but I would recommend having a go at this exercise in your own time if you can, to extend the model that you built in exercise 1. Maybe get together as a group and see if you can have a go at in your groups to have a go at this. But think about how you would use what we've just talked about this afternoon to extend the model you built earlier, so that you're also capturing this aspect here, where alongside people coming into the GP surgery physically, you've also got calls coming in every 10 minutes on average, and a receptionist who's also doing the registration is also answering these incoming calls every 10 minutes. You don't have to worry about adding any results for any of that. All we're interested in here is how this drains some time away from the receptionist. So before, there was never a queue here, because it only took 2 minutes on average to register them. They're coming in on average every 3 minutes, so if there was a queue, it was negligible. But now suddenly you may have a problem, because now you've got people that are only coming in every 10 minutes on average, but then they're spending on average every 4 minutes on the phone call. And on top of this stuff that's coming in, that might then start to cause some queues for your receptionist. Also then think about how you're going to add a warm-up period of 3 hours before the 8-hour result collection period, and then also build in some functionality to run the simulation multiple times. So have the simulation run 100 times and take average results over those runs. What I will do, I will post up the solutions for all this with the rest of the stuff as well at the end of this session. But have a go at that yourself first before you look at the solution if you can. And I highly recommend you do this, because it'd be worth, a lot of you I think will be probably looking at discrete event simulation models for some of the stuff you're doing. And if you are, then being able to do this kind of stuff is going to be really important. So you've obviously picked up the skills, all the core skills today on how to build a discrete event simulation model. And this will give you the practice to be able to, how you build in this sort of extra but important stuff where you're capturing additional parallel activities and parallel generators, and where you're including warm-up periods, and where you're running the simulation multiple times, particularly warm-up periods and multiple runs of the simulation. Very important. I would expect most of your models to incorporate those things when you're building these for real. Okay, so I'll close off there, because I think trying to set you off for 8 minutes to do this exercise is completely pointless. But as I do have a look at that, and I would encourage you. So that's the last of the core sessions for this module, for the discrete event simulation module. But I would advise, if you are interested in doing discrete event simulation, to come along to the one in a few weeks' time, where I'll basically go through how to do this using an object-oriented framework. So I'd encourage you to check that out. Next week, we've got a couple of sessions. So next Tuesday, let me just check the calendar, but I believe you've got some network analysis stuff coming up next week. Let's have a look. 9th. Yeah, so next week you've got 2 different sessions. Okay, and this is going to be the case for most of your stuff in the upcoming sessions now. You'll have a different session in the morning and a different session in the afternoon. Most of them will still be taken by me, but you will have a couple of other trainers as well for some of this stuff, including next Tuesday morning, where Sean is going to be introducing you to network analysis, which will introduce you to some of the fantastic stuff you can do using network analysis for capturing whole systems and the dynamics of whole systems. And then in the afternoon, I'm going to take you through an introduction to AI and machine learning. And I'll take you through some of the sort of key concepts. And I've got a very fun, hopefully a very fun exercise for you to do to practice that, where you try and second guess my film preferences. So a bit of fun to come up for that particular afternoon session. Again, a reminder as well, you need to be now thinking about your projects. Apologies if you didn't see the message I posted earlier. My apologies, I did get the date wrong this morning. It is the 29th of November is the deadline for submitting your project pitches. I will be providing more information in the next couple of days about what you need to do. I'll also post the links to the videos of the successful pitches from last year, so you can see what we're after. But it's just something very simple that is a quick 2-minute pitch of what you want to do, the methods you're going to use, and why you want to do it, and what impact you think it's going to have. And that's basically what we need to hear. And that needs to be by the 29th. We will then go through those on the 29th and select a number of those projects to be taken forward. I would encourage you all now to be talking to each other on Slack in order to, if you want to look for potential collaborative projects, now would be a good time to be starting to talk to each other about some ideas and sort of bouncing ideas off each other. It'd be great to have some great collaborative projects upcoming for this stuff. But also bear in mind that you're still going to be learning. So obviously we've only covered discrete event simulation so far. So over the next few weeks, as you start to become exposed to this stuff, hopefully that will start to fire off some ideas for you as well. And it may be worth at this stage going back to the very first session, session 1A, looking back through the slides for that, where I sort of gave a very a quick sort of 1 to 2 slide intro of each of the methods that you're going to be covering in the next few weeks to give you some idea about what this stuff can do. Any questions about any of that? No? Great. Okay, in which case I've probably tired you all out now. So hope you had fun today. Hope that was useful. All go away very proud of yourselves that you've managed to build a simulation model. It's a great achievement. So big pat on the back. And I look forward to seeing you next week. I'll post up information shortly, maybe tomorrow, about the stuff you'll need to download in preparation for the my AI session next Tuesday. And Sean will also post up some information soon about the stuff you'll need for his network analysis session. Until then, have fun. If you have any questions, do post them on Slack. And as I say, do start talking to each other, start bouncing some ideas off each other about potential projects. And I look forward to seeing you next week. Until then, goodbye.